So Andrew, if you're here, you can begin to share the screen for the planning.
Okay.
After you start, just give me like 1 minute. I just want to make sure that the stream is working.
Okay.
I think the stream is going, but yeah, we'll see. Okay. Is Ryan here? Andrew, have we actually announced who the finalists are going to be?
Not yet.
Not yet. Okay. So I will make that announcement now. So our top 3 scoring teams in decreasing order of rank. Ranking number 1 is Team Sigma. Ranking number 2 is Team Epsilon. And ranking number 3 is Team Anti-Quarks. So we will begin the planning. So could you guys take some time to talk with your teams and let us know which problems you will be presenting? So in terms of the jurors for the finals, any juror that is actually here can choose to judge. If you're free to judge, just, I don't know, type something in the chat and then we will include you in the planning. Yes, this is Jim. Yes, this is me. So we are running quite late. So yeah. So Andrew, you've got the planning?
Yes.
Yes, okay.
So you've announced 3 teams?
I have announced the 3 teams. So Team
Sigma?
Epsilon wants to do Spindrift.
Okay,
and then
that's going to come next. We first have
afterwards,
to
right?
input the teams. So Team Upsilon, Team Sigma, and Team Anti-Quarks.
Okay, is Dave here ready to do some timing, or is Andrew just going to be doing the entire timing?
Dave will do the timing. I've assigned it to room E, which is Dave's room.
Yeah. Can you hear me?
All right. Yes, we can all hear you.
Awesome. Okay.
You can change your name to, I don't know, like Dave or something.
Okay, sure.
Okay, cool. I think our stream is going fine. Yeah. Not sure if this 1080p actually works. Maybe. It's fine. We'll have a high quality recording of it anyway. All right. So to the jurors that are judging, this time we will have all 3 roles. So that's the reporter, the opponent, and the reviewer. So you will be using the entirety of the score sheet.
Okay, so I see a small lull in the people saying that they can judge. So I'm going to read all the names that I've checked in, and if any jurors whose names were not called want to judge, just write in the chat. So
Or
I
actually just
have-
speak up. That would be
Yeah.
more convenient for us.
Yes, we Ms. Vanderkamp, we have not included you as of now, so we're good on that part. So we have so I'll just scroll through the list, and if you don't see your name
Yeah.
checked and want to judge, then
So I can read out the names, I guess. We have Daniela, Carlos, Neil, Darby, Jesse, Kyle, Shito, I think, and Abdullah. Anyone else?
Also Michael.
Oh, also Michael. Yes. Anyone that wants to judge that we have not called out? Okay. That's fine, it seems like. All right.
Okay. Then we have our teams, Team Upsilon, Team Sigma, and Team Anti-Quarks. And we also chosen our room E, and we'll be submitting this now. So the next thing we're going to do is we are going to be accepting and activating the plan. And then I've published a plan, so now everyone should be able to see it when they navigate to home and click on final. You see all of the info over here. So yeah, I'll give Dave a moment to set up, and yeah.
Yeah, Andrew, I don't see it on my end.
Um,
So I'm going under final match, and it's telling me invalid access.
oh wait, you're not, okay, change to,
Oh, V007, right?
yes.
Okay, got it. Yep, that's good. Okay.
So then, I don't remember the placing. So yeah, just select which place they were. Oh wait,
So
we already have it
Sigma,
here.
So Sigma is first, Epsilon is second, and then Anti-Quarks is third.
Is that correct?
That should be correct. Yes.
Okay.
So problem-wise, Team Epsilon, you guys have decided on Spindrift. Is that correct, Martin?
Yes, we confirm.
Okay. And what about Team Sigma? Well, you guys get the first choice. So, okay, Sigma, you guys are doing a rebounding capsule. Okay, that's great. And what about Anti-Quarks?
Bead dynamics?
I don't think.
So Anti-Quarks, to confirm, you guys are doing beat dynamics. Is that correct?
Yes.
Beat dynamics. Andrew, we've got that.
That would be Dave.
Or Dave,
So-
we've got that.
Sorry.
Yes.
Okay.
Okay.
So
Cool.
Team Upsilon is
Team Epsilon. Team Epsilon is Spindrift.
like which
Yes.
letter is that?
Oh, Spindrift. Okay. Okay. You think when we chose the problems, we would know the exact letter. So Spindrift is D.
Okay. And then Sigma is doing
Sigma is doing rebounding
rebounding
capsule,
capsule, which is
and that is I.
okay. And then Anti-Quarks is B dynamics, which is
Dynamics, which is C.
okay. Got it. Yep, that's good.
Okay.
And then I have to check off on the jurors. We already checked that before, though, right?
Let's just do a final check to just to make sure that we're all here.
Okay.
So Daniela, you're here, right? Yes. Carlos,
Yes.
Neil.
Yes.
Okay. And then we have who else? Dave, you.
Darby's here.
Darby's here. Okay. And
Jesse.
okay.
I'm here.
Okay. And, Dave, you can just continue to call out the names.
I think Dave just may have had technical difficulties,
Dave had technical difficulty.
and he's, I think, logged out.
He's logged out.
I got kicked out of the Zoom meeting.
What? Okay.
Yeah.
So,
Jesse.
yeah, Jesse's here, and then
Kyle.
Kyle. I think Kyle is here.
Shito.
I'm here.
Okay. Abdullah.
Abdullah's here. Michael's here too.
Okay. Awesome.
Yep.
All right.
Very good. And then submit.
Start. Yep.
Okay. Andrew.
It's okay. That's just because. Okay, why don't I do this? Okay, wait a moment.
So before everyone sees the amazing presentations by these three teams, we have to build some suspense, eh? Just, yeah.
Okay, so just wait a moment. Yeah, so I'll take care of this. So here we go. Okay.
What prize does the winning team get?
They will get gold medal, which we
And-
will mail it to them afterwards. Yes.
Anything else like food?
Food. Yes. As Carlos mentioned, honor. Yes.
So just to confirm, first place was Sigma,
Sigma, correct.
and then second Upsilon,
Epsilon, correct.
and then third Anti-Quarks.
Anti-Quarks, right?
And then Upsilon chose
wanted
which
to
letter?
Epsilon wanted to do It was we will Spindrift, which is D.
D.
I believe
Okay.
it was D, I, and C. Right. Rebounding capsule was Sigma, right? And then B dynamics is Anti-Quarks.
Okay, and then all the drawers are here.
All the drawers are here.
Okay.
We can get started, hopefully.
Okay. Yeah. So we're good. I'm going to log out now, and let Dave take over.
Yep. So if I go to final match, yeah, it works for me. So whenever you guys are ready. So we have to choose, so whenever the teams are ready, we can choose whoever's reporting, opposing, and reviewing. Can the teams just like type it into chat, like your team name and then who's doing the role in this round?
Sorry, maybe have a second. Our team leader is not feeling well.
Yes, definitely.
What's the live stream link that we're using for this?
I can share it in the chat.
Please.
Sorry, so this round, the reporter is Team Sigma.
Okay, so due to some unforeseen circumstances, one of the teams just needs a few more minutes, and then we'll start soon. Thank you.
So Team Sigma, do you guys have your choice of who is going to be going on stage?
Wait, I already sent it in the chat earlier.
Okay, cool. So we have, okay, got it. So Dave, is Dave there?
Yep, I'm here.
Okay, so let's enter in the student names.
Okay,
So we have Daniel from
Yep.
Sigma.
Okay,
We have Epsilon Alan,
right.
and then
Anti-Quarks.
Kevin. Yes.
Isn't this reverse order though? Because Team Sigma is first rank, so shouldn't they be reporting last?
I also thought that
Just curious about
we
too.
would be opposing Anti-Quarks.
Yeah, Jim.
No, that is something to do with the system, the way that you've selected the three, I think, in which order. But I think it will not be possible for us to actually go back and change that. So we will just proceed with this order.
Are we good to begin then? So it's Daniel for reporter, Alan for opponent, and Kevin for reviewer. Okay, then I will submit. Okay.
Who coded this?
All that credit goes to Andrew and his team.
Excellent.
Okay, Jim, are we good to begin?
Yes, we are good to begin.
Okay, and then so Team Sigma, you have 5 minutes to get started. Okay, Team Sigma, you may start.
Can I start? All right, thank you. Hello, everyone. My name is Daniel Yang, and today I'll be presenting problem I, rebounding capsule for Team Sigma. So the problem statement reads as follows. A spherical ball dropped onto a hard surface will never rebound to the release height, even if it has an initial spin. A capsule-shaped object, i.e. a tic-tac mint, on the other hand, may exceed the initial height. Investigate this phenomenon. So some relevant parameters that we identified are the drop height, the initial angular velocity, the capsule material, the capsule dimensions or shape, and the surface material of the hard surface you are rebounding the capsule on. So here's a quick overview of my presentation. I'll be going into the reproduction of the phenomenon. I'll be talking about my experimental setup, my theoretical models, and the key parameters and how they affect this phenomenon. So first of all, let's get into my experimental setup. So this is my experimental setup. We have a backdrop. We have two backdrops with a support beam and a capsule spinner, and also a hard surface. So here's the capsule spinner with a side view. We have circular discs with an adjustable screw and padding. And of course, we have our capsule in the middle. So here is the phenomenon in action with everything labeled. This video is slowed down 8 times. So if we are to zoom in on this section and analyze the motion of this capsule for this particular instance more closely, we can observe that there is a first bounce, and then it reaches a high H1, then it bounces a second time and reaches a high H2. And do note that the fourth bounce is higher than the third bounce, which is partially what we wanted to observe in the first place. So in preliminary observations, here are some preliminary observations. In this particular video, we note that the bounces decrease. So the first bounce is higher than the second bounce, is higher than the third bounce, as expected. However, we do observe that sometimes it is possible for the second bounce to be higher than the first bounce, or in some extreme cases, it is possible for the third bounce to be higher than the second bounce, which is also higher than the first bounce, as demonstrated in this video. So the measurement method we used was tracker. So what we did is we simply tracked the bounce locations and the trajectory peaks to get a sense of how high the capsule bounced each time. For measuring physical parameters, we used a meter stick and a caliper and analytical balance to measure our tic-tacs. Now, one question you may have is, when we spin the capsule spinner, does the tic-tac actually spin at the speed the capsule, does the tic-tac itself actually spin at the speed the capsule spinner is spinning at? And so to do this, we can track the location of both the capsule and the spinner in the following video. And we obtain the following data, which show that the angular velocity of both the capsule and the spinner are roughly the same. Now I'll be moving on into a qualitative explanation of the phenomenon. So we do note that the problem statement says that when a spherical ball bounces off a flat surface, it is impossible for the sphere to rebound to its initial height. We see that when there is no rotation, this is due to the fact that there is a coefficient of restitution E between the surface and the ball, and so the ball will successfully bounce lower and lower. And even when there is a spin, the only force during the impact is friction, and so there's actually no impact on the vertical velocity, and so this ball will also not be unable to rebound to greater than the initial height. However, for a capsule-shaped object, when it has a very large initial velocity, let's consider hypothetically a situation where the capsule rebounds and it has a much lower angular velocity with respect to the initial angular velocity. Assuming conservation of energy, we can see that essentially what happens is that this rotational energy, the rotational kinetic energy in the capsule is transferred into translational kinetic energy upwards. And so this capsule may actually rebound to a height that is higher than the initial height it was released at. So next, let's move on into our theoretical model. So first, we have to recognize that our system is inherently chaotic and it is very random. And thus we choose a slightly different way to model and take our measurements. So conditions for chaos are the typical conditions for chaos are as follows. And we see that it indeed does meet the chaos conditions, and it's thus impossible to really accurately predict the motion beyond certain limits. More specifically, I would like to draw your attention to the highly sensitive initial conditions of the system. For example, if the angular velocity were to be changed a very slight amount, over the time it takes for the capsule to drop to the ground, that may result in a significant angle change in the contact between the capsule and the ground, and thus the capsule may in fact rebound in a completely different direction. As such, we consider a more stochastic model where we randomly select values for the initial angle and simply model the distribution of rebound heights instead of trying to model an exact instance of this phenomenon. So let's move into our theoretical model. First of all, we'll model the trajectory of the capsule. So the geometry of the capsule is as follows. We assume that it is a cylindrical body connected to two spherical caps. And some key assumptions we make are that the capsule will not chip or deform significantly, angular drag is negligible, and rotation is on a 2D plane. So when the capsule is in free fall, i.e. it's not colliding with anything, and of course we have the force of gravity and we have the drag force. And so we can write the motion equations of the capsule as such, where I is the capsule moment of inertia. So more specifically, we can split this capsule into a cylinder and a hemispherical cap. And so when calculating those moments of inertia, we can integrate to find the moments of inertia of the cap and the hemispherical cap and the cylindrical body, and combining them together and taking account to the shifted center of mass, we can get the following equation for the moment of inertia of the capsule, where mcy is the cylinder mass and mhs is the hemisphere mass. So next, let's justify one of the assumptions we made earlier about air resistance, that angular drag is negligible. And we can see that indeed when we calculate the torque due to air resistance, it's roughly on the order of 10 to the -8, which should be negligible. So next, we move into collision resolution. So with our capsule as follows, we can keep our assumptions the same, except this time there's now a contact surface, and we assume that there's a very small collision time. The free body diagram is as follows. We have a normal force, a friction force, and a gravity force that is acting on the capsule. And so we can find there's also a coefficient of restitution of this capsule since it will necessarily lose some energy in the collision with the ground. And so we can find this coefficient of restitution based on a drop that happens to be aligned with the vertical in this video, and we can determine the following value for the coefficient of restitution. So the force equations can be written as follows, and integrating, we can solve for the impulse acting on the system, which leads to the equation below. So to resolve the collision itself, we can use the impulse method, which is essentially we act an instantaneous impulse on the capsule to resolve the collision and set it on its new trajectory. And so essentially just writing out the motion of the two objects and defining their relative velocities, we can find that we can use impulse to connect the pre and post collision velocities as follows, and we can solve for the impulse. And since our surface B, the secondary surface, is actually a solid wall, it simplifies to this. Now we can actually simulate this. Process. So we can combine our two theoretical models together and simply just simulate it as represented in this flowchart. So a sample simulation, this is really just arbitrary parameters, but it shows that sometimes we do indeed see that like the third bounce would be higher than the second bounce, or similar things like that. And so the actual simulation process, since we want to investigate when a dropped capsule may exceed the initial height, we can simulate dropping the capsule at many random angles and angular velocities and compare those distributions to our experimental data. And so moving on to our key parameters, we investigated the rebound height, the probability that the first rebound height is greater than the initial rebound height, And we also investigated the probability that, say, like the second rebound height is greater than the first rebound height, and so on, since they're effectively the same phenomenon. So we saw, we investigated drop height, initial angular velocity, the coefficient of restitution, capsule shape and dimensions, and the surface coefficient of restitution, and we saw they had the following correlations with the two variables on the right. So for the first rebound height, so this is a cumulative frequency distribution of the rebound heights that we observed after 104 trials of dropping the capsule and tracking it to determine where its highest location was. And we can graph this along with our theoretical model, which closely agrees for the most part to our experimental data. So then we also investigated successive rebound heights. So for example, here, we investigated the first, second, third, and fourth successive rebound heights of the capsule. And so we saw that generally there are, the rebound heights were lower as expected. And so the next one part of the problem that we were told to investigate were the chances that the capsule would bounce higher than before. And so with our data for the following section, we determined the following probabilities that the capsule may bounce higher, and we see that's actually pretty significant. It's a pretty significant chance that the capsule bounces higher than before. So in conclusion, we had a controlled experimental setup and measurement method to track the motion of this capsule. We provided a thorough qualitative explanation and a thorough quantitative explanation and simulation of the process through which this tic-tac bounces. And we also investigated key parameters and obtained lots of experimental data to support our conclusion. Here are my references, and thank you very much for listening.
Thank you, Daniel. Okay, now we have 2 minutes for opposition questions.
Okay, I'm going to get started. Did you account for any horizontal kinetic energy within your experiments?
Yes, the model doesn't include the horizontal velocity of the capsule.
Okay, and were you able to correlate the difference in horizontal velocity after a bounce?
Yes, from here, we can definitely determine the difference in horizontal kinetic energy before and after a bounce. Yes, I think so.
Okay, did you consider any other non-conservative forces like slip, friction, or air resistance?
So we considered air resistance throughout the fall, and generally the contact time is very small, so there's really no need to consider sliding unless you're
Okay. Did you consider any horizontal kinetic energy within your experiment, within your simulation?
Yes, I think you addressed this question earlier. It does consider horizontal kinetic energy.
Okay, thank you. Do you have evidence of experimental results being correlated with your simulation, or do you have can you verify it?
The distributions or a single trajectory?
A single trajectory.
Single trajectories are very hard to actually model due to the chaotic nature of the system. I already explained that.
But given the initial variables, could you not input those into the simulation?
You definitely could, but they would probably deviate right after the first bounce even.
Okay. And what is the coefficient of restitution based on within your thing? Did you measure it? How did you measure it?
Yeah, it was measured experimentally.
Oh, okay. All right. No further questions.
Okay, thank you. 3 minutes for the opponent to prepare now. Okay, you may begin your opposition, 4 minutes.
Okay, this is my opposition's presentation for rebounding capsule. I'm Alan Lian. I'm just going to go over the problem statement again for some clarification. A spherical ball dropped on a hard surface will never rebound to the release height, even if it has initial spin. A capsule-shaped object, i.e. a tic-tac mint, on the other hand, may exceed the initial height. Investigate this phenomenon. I've identified 3 tasks that I felt were necessary in order to fulfill the problem statement. So one was accurately recreate the phenomenon and collect relevant data. Task 2 was create the theory that explains the type of motion. And then number 3 was verify your theoretical model with experimental data gathered from your from the experiments. So in the reporter's report, he brought up he first talked about the experimental setup and how all of that was calibrated and worked. And then he went through some tracking of the actual objects, gathering data, and some preliminary observations within it. And then he went through some equations of the prediction of a trajectory, and then went on to simulate the experiment with software. So some merits and next steps within his presentation. So first, there was a clear analysis of experimental videos. The setup and the geometry was well done, and there was very good labeling, and it was very clear. He was able to describe, to observe the bounce and the phenomenon very well and explain that. Another merit was the theoretical model that he went through, the conservation of energy and the moment of inertia, and all of his equations were very well developed throughout the thing, and and some possible next steps that I'd like to address. So some of the parameters that he mentioned within his first slides weren't actually addressed or changed within the experiment, and there was no evidence of them actually creating a difference in result. There was limited experimental measurements correlated to the actual data, and then correlated to the theory. And then there was also a sort of an exclusion of non-conservative forces that we'd like to talk about, although isn't too threatening, too serious. So in the discussion, following discussion, I'd like to talk about the coefficient of restitution and with how he calibrated the coefficient of restitution and some other possible factors and some non-conservative forces that perhaps he didn't that weren't considered. And then I talk about some varying parameters, initial conditions, and the parameters that he wasn't able to address within his experiments. And then perhaps some feedback on a better designed experiment, and then a clarification of some of the data and graphs that he showed us. So, thank you.
Okay, so you can start
I'd
the
like
discussion.
to invite the reporter up. Sec.
Hello, would you like me to present my slides again?
Yeah, sure.
All right.
Okay, so first, were there any, for example, in your key parameters slide, so your identification of the parameters, how many of these were you able to actually vary during your experiments?
So in the actual experiment, we only varied drop height and initial angular velocity.
Okay, so those are, yeah, so those are the ones that were viable within your experiment. Is there any other ones that you could have done, a different capsule material or changing the surface?
Capsule material, capsule shape and dimensions, and surface material, these are things that with enough effort can be changed. However, for our experiment, the way we decide to model it as more of a random process and trying to model the distribution instead, this requires us a very large amount of data, and so we opted to only consider one capsule to not have so much work on our hands.
So yeah, we agree, and we agree, and it is very difficult to measure so much data. However, it would have been nice to have seen some indication of a material change that would have resulted in some difference in experimental data. For example, if you change the capsule dimensions, I noticed in your experimental setup you had padding and a screw, which is evidence that you can change the width of it. So so it would have been nice to see you construct some like maybe buy a larger Tic Tac or something.
Yeah, by changing the capsule material or capsule dimensions, we can change the coefficient of restitution between the capsule material and the surface, and that will definitely affect the experience.
Okay. Yeah, we agree. So how would you say the moment of inertia would change relative to like the different capsule size or dimensions?
Well, if you just scaled up your normal capsule, it wouldn't actually change. But it depends on the distribution of mass within the capsule and how far it is. Like for example, if you had a longer capsule, the moment of inertia would increase.
Yeah, we agree. And if we were able to measure this, it would be preferred. Also, what do you think the result of a perhaps like a softer surface material or a surface material with more friction would cause?
All right. Yeah. So the reason we chose to investigate like the reason we made our assumptions with our like small contact time and like the rebounding process is since the problem statement says to drop it onto like a hard surface. However, if we were to replace this with for example, a softer surface or a softer capsule that may allow deformation into the capsule, this process would be a lot more complicated. And frictional forces would play a much larger role in determining the final angular velocity the capsule would rotate after bouncing, say, once.
Of course, and the amount of time of contact would also be varied, so it would greatly change the trajectory. What do you think the grip of the material would have on the horizontal velocity or like movement?
The grip of the surface material? Yeah, all right. So if you have like a very low grip surface material, if it were almost frictionless, then there would be a very high possibility for the capsule to just like to slide after rebounding. But when you have a surface material that is say like rougher or just able to grip more, that doesn't happen as much.
And also it probably propel it further in the direction of the angular energy. Okay. So we're going to move on quickly to your coefficient of restitution. We're wondering if you have like data that shows the correlation between the energy before and after the bounce.
Yeah, so it's really just so basically when we took our like 100 trials, there were some trials that happened to be very close to bouncing exactly like vertically and having essentially no angular velocity after. So this is an example of one of the trials. If you watch very, very closely, you can see the Tic Tac there. And it bounces nearly straight up. And so we can determine the ratio of energy. And so we can determine the energy loss, and that's the coefficient of restitution.
Okay, how would your starting, like your variables for the, for your like the variable, the parameters you identified previously affect the coefficient of restitution?
So how would the parameters affect the coefficient of restitution? Wait, so like drop back. Okay, so I mean the coefficient of restitution will be solely dependent on the material of the capsule and the material of the surface. There also may be so something else that that we might be able to consider in a future model is that the coefficient of restitution may actually depend slightly on the velocity of the impact, and so that's certainly something to investigate.
Yeah, so we agree.
It depends on the capsule material and the surface material.
Yeah, so we agree, obviously. So if we could vary the capsule material and the surface material, it would create like different coefficients of restitution, and you could perhaps get a higher bounce or something along those lines. Okay, okay, so I'm going to move on to some of your graphs. I just wanted to clarify some problems. On slide 14, why is there a negative value for your?
Yeah, it was okay. So the thing is the capsule. So when I was tracking the capsule, it's like it was at that point it was just exiting the capsule spinner, right? So it was a blur, and it wasn't actually very clear what the angle was. So when we marked it, it just happened to like seem to turn the other direction. But the overall field velocity is just like that.
So this is a form of error. And do you have error bars on this?
On this graph, no.
What the error would be in this case, or the margin?
What would the error be?
Pardon?
So the error would be based on the measurements of, the error would be based on the measurements of the size of the Tic Tac and the size of the size of the spinner. But also some error here might be due to the resolution of like the video itself, because the Tic Tac is very small and when recording, kind of hard.
So there's a couple places of error that could need correcting. Well, I'm wondering why there's a deviation between the two trends.
Like why there's an offset? The offset is just like the actual angle itself that we tracked it at. The angular velocities themselves are very close.
Can you hear me?
Yes, we can hear you.
Hello?
Yes. Hello. Can you hear us? Can everyone hear us?
Pause the clock. Pause the clock.
We can hear both of you.
Okay.
Yeah, we can hear both of you.
I can hear you.
Okay. I'm just gonna. Can you mute? I'm gonna switch on to. Sorry. Sorry. Is there echo? Okay. So quickly, could you go to slide 43?
43. Yes. Mm-hmm.
And show the graph. Yeah. Can you explain the deviations between the theoretical and the experimental, or like the error, and if there are error bars, and what would they be?
Yeah. So there are error. Okay. So first of all, I'll address the error bars. The error bars are, but they definitely are there. It's the error in the rebound height, and this is just the error in the measurement of like the height. So it's very small because of the calibration tool we used. And then the deviation at the endpoint, okay, so some random deviations along the curve are simply due to like the random nature of the process. We dropped it 100 times randomly. It might not match the theory exactly. And the deviation at the endpoints may be due to a different coefficient of restitution based on how, like, there might be a slightly different coefficient of restitution based on how the capsule exactly impacts the surface. The surface.
Okay. Yeah, we agree. It's very difficult to have a precise and like consistent coefficient of restitution, so that would make sense, and it showed in our experiments as well. Could you go to slide 44? And I just like to wonder, why are they lines instead of a scatter plot?
Okay, yeah, I could have plotted it as a scatter plot, except I think actually for like cumulative frequency graphs, it's probably fine to plot them as lines, but yeah, I could have done it. I definitely could have done it as a scatter plot.
Okay.
It's just matplotlib.
Yeah, see, I think it would have made a bit more, been a bit more clear if it were scatter plot. And how does the theory like sort of verify this graph and like the?
There is no really theoretical verification of this graph. This graph is actually a continuation of the previous graph.
Yeah.
It's just with the second rebound, the third rebound, and the fourth rebounds for those that we could see.
Okay.
And yeah, there's no really theoretical section to verify this yet.
Okay, I think that's it.
All right,
thank you for your discussion. And I'll go on to conclusions.
Okay, thank you. You can start your concluding remarks, or sorry, your summary.
Okay, so in our discussion, we talked, so in our discussion, we talked a lot about, some of the varying parameters at the beginning, and some things that he could have, changed that he mentioned within his initial parameter slide that he perhaps didn't address within his measurements, and some things that we could do in the future. to actually address these parameters and see their effects on the bounce itself. And then we address some of the error bars and mistakes within the scientific the graphing, and then explained, and then we clarified some of those. And then we talked a bit about the coefficient of restitution and what different variables would have based on the bounce effect based on the bounce height and other results. Thank you.
Thank you. 2 minutes for concluding remarks. Oh, sorry. Questions from the reviewer. Sorry.
All right. So to the reporter. So you assume that the Tic Tac has a cylindrical body when in fact it isn't. It's somewhat like a square shape.
If you look at the images of the Tic Tac, it's very close to a cylindrical body with 2 hemispherical caps attached to either end.
Do you agree that the shape of the drop cap will affect the experimental results?
Yes.
And mathematically, capsule is a sphere of cylinder. Do you agree that Tic Tacs are not capsule shaped?
No, wait. There is no like set definition of exactly what a capsule is, and a Tic Tac is pretty much a capsule.
And does the opponent agree as well?
Yeah, although there are variations with a Tic Tac to a specific capsule, a Tic Tac is given in the problem statement, and so verified, like you can use it.
And to the reporter. So can you explain the shape of the velocity graph? Slide 39.
There was no velocity graph. I'm not sure what you're referring to.
Slide 39, maybe?
That's a Y position versus time graph.
All right. Actually, do you mind screen sharing?
Sure. This is just an arbitrary simulation because we didn't determine the exact parameters for the Tic Tac. Can you see my screen?
Yes, I can see your screen. So why isn't the Y position 0 on the first and second bounce?
The parameters are arbitrary and it's not like zero necessarily. The graph is literally just a visualization of what our model has outputted.
And
so just to visualize that, like our model does predict that sometimes the rebounding heights can be higher than previous rebounding heights.
So there's no representation of.
We don't actually have a trajectory prediction that is verified experimentally. No.
And to the opposition, you mentioned some other key parameters the reporter missed. What do you think is the most important one that impacts this phenomenon?
I think the most important. Wait, pardon. The ones that he didn't address, or he did.
The key parameters that the reporter missed.
That they missed. So I think one of the most important ones is the the material and the dimensions of the capsule itself, because those were addressed, and they would have a pretty large effect on what the bouncing motion and the resulting vectors.
And what do you think is the overall most important?
Probably the rotational velocity, because it has the most effect on whether or not the phenomenon.
And does the reporter agree with that?
Yes, I do agree that.
Short answer.
Velocity. Yeah.
Okay,
yes.
Thank you. 2 minutes for the preparation of the reviewer. Okay, preparation time is up. For the reviewer, please begin.
Sorry, can you give me a minute? All right.
So from now on, like to all the teams, please have your screen shared before the timer runs out. Thanks.
All right, rebounding capsule. I'm just going to reiterate. A spherical ball dropped on a hard surface never rebound to the release height, even if it has initial spin. A capsule-shaped object, on the other hand, makes the initial height. Investigate the phenomenon. Some tasks qualitatively explain the bouncing behavior. Construct a controlled, repeatable experiment set up to predict trends in relation to various parameters. Investigate the effects of key parameters on the motion, for example, coefficient of restitution, rebound height, linear and angular velocity. And task 4, theoretically predict the motion of the capsule. So summary of the report, the theoretical analysis that the reporter gave was trajectory, collision resolution, and simulation. And then some experimental confirmation, the rebound height. The rebound height was confirmation for the trajectory, but there was no experimental confirmation for the collision resolution and also for the simulation. And I'm just going to list some merits and possible next step for the reporter. And then so the phenomenon was replicated, so we can see like the tic-tac bounce higher than the original height. And then the experimental setup was solid. It was able to like take into account various different key parameters. However, also there are some possible next steps. For example, limited experimental verification. So I think the reporter mentioned something about what possible deviate from the first bounce, but there was no experimental like verification to back that up. And then there was a bit of lacking error analysis, and certain parameters are also lacking. So summary of the opponent. So the key insights included the experimental setup, the tracking and the preliminary data, the prediction of trajectory and simulation. And so I guess, so for the discussion analysis, the points raised by the opponent was about the capsule dimensions. The reporter's response, they talked about the change in coefficient of restitution. So I agree with the opponent because the reporter, it wasn't directly answering the question about the capsule dimensions. And the second discussion analysis was the surface material and the time of contact, which was the point raised by the opponent. And the reporter's response was softer surface, softer capsules allow for deformation, and it's a lot more complicated. And I agree with both because with like a softer surface, right? There's like a the impulse is like greater. There's like a longer time for the capsule to kind of deform into like a surface, or maybe softer capsules to deform. And I guess that's it.
Okay, thank you. 2 minutes for concluding remarks now.
All right. All right. So to conclude, what we did in our presentation is we constructed a stable experimental setup to vary both the angular velocity and drop height of the tic-tac, and we measured it with a reliable tracking software. Then we provided a detailed qualitative explanation and theoretical modeling of the motion of the tic-tac, and also ended up simulating some of this motion as well. And we also investigated some key parameters affecting the rebound height of the tic-tac, and also had a significant amount of experimental data to show when the capsule rebounded higher than its initial height. So some points that were raised by the opponents were that, and by the opponent and the reviewer, were that the parameters mentioned weren't addressed. There were limited experimental measurements, and there were exclusion of non-conservative forces. With respect to the first point, we did indeed qualitatively address many of the parameters that we didn't actually vary in the experiment. just like the reviewer also stated. As to the point on limited experimental measurements, we do agree that there could have been improvements in the amount or the exact type of experimental measurements made, perhaps to quantitatively verify the trajectory of the particle. And we also addressed non-conservative forces. So overall, we believe that we have successfully fulfilled the tasks identified by both the opponent and the reviewer in this problem. And I would like to thank the opponent and the reviewer for their discussion and comments. Thank you very much.
Thank you. 5 minutes for questions from the jury. So if you want to ask a question, just unmute yourself. And if it starts to become too chaotic, then we might use the chat later on. But yeah.
Hi, thank you to all three parties for your presentations and discussions. I would like to ask the reporter to comment on the magnitudes of the normal force and gravitational force on slide 31 of their presentation.
Oh, yeah, so the arrows drawn weren't actually like indicative of the respective magnitudes of the normal and gravitational force. In reality, the normal force is much, much, much larger than the gravitational force, especially due to the small contact time we observe during the bouncing on a hard surface. So the arrows aren't actually to scale. The normal force is much, much, much larger.
Okay, thank you.
Sure. I have a question for the reporter also. In your slide 19, you can pull it up if you want. You talk about this experiment having 6 degrees of freedom. So what are they?
Well, there are the three translational axes that the capsule can move, because the capsule is actually a 3D object, even though we ended up modeling it as not such. And there are also the 3 rotational degrees of freedom of the capsule. Yeah.
Okay. Do translational velocities count or no?
Like it's just the translational motion, like the directions that the capsule can move, right?
So you said that there are 3 position degrees of freedom and 3 rotational velocities?
Yeah, so three rotational, yeah. Yes, basically.
Okay, sure.
I had a question for the opponent. So there was a long discussion on coefficient of restitution. So I think it was reported by the reporter that the coefficient of restitution depends only on the materials in contact, and that it's less than 1. So then when you observe a bounce that's higher than the previous bounce, does your coefficient of restitution change to be greater than 1? Or what's
No,
happening?
it doesn't.
So
what happens is you have to consider all of the energy that is used, right? There's also, when you're entering your initial height to the first bounce, you have your rotational, translational, and gravitational energy, right? And when you're converting that to your second bounce, which is higher, the rotational energy is lost, and the some of it is lost and converted to potential energy, and some to vertical and then potential energy, and some of the horizontal translational energy is also lost. So in that sense, the ratio of energies between the first bounce, between the vertex of both bounces is still the same as the coefficient of restitution.
My question, I understand that the energy balance can be taken into consideration. My question specifically because coefficient of restitution is not defined with energy, it's defined with velocities. So one big question is how do you make peace with the fact that velocity, which should actually be E times the original velocity, is increasing, because of which it's bouncing to a greater height?
Well, the energy and the velocities are proportionally correlated in this situation, so it's the same thing, but just on a different, by a different unit, right? So even then, your rotational velocity is smaller and converted into translational in the z-axis.
Right.
I think the reporter wants to answer, so go ahead.
I can add something. So essentially, when we have a high rotational, when there's a high angular velocity, the relative velocity between the point of contact of the collision and like the surface, it still ends up greater, even though the actual final translational velocity might be greater afterwards. But like the relative velocity between the point of contact before can be greater due to the rotation of the capsule.
Any thoughts from the reviewer for this?
So I've seen like the coefficient. So I've seen like the coefficient of restitution been modeled like differently. Like sometimes they like model it with like velocities, and other times they model it with kinetic energy. And so so I guess like I'm going to have to agree with the reporter, because like for like the coefficient of restitution to be greater than 1, then technically the velocity, then technically the velocity, the rebound velocity is going to be higher than like the incoming velocity, like the y component.
I have a quick question for the reporter. You mentioned at the start that one of the reasons why you went with the methodology you did was that there were 6 degrees of freedom. Do you think that there are really effectively 6 degrees of freedom? I mean, I agree completely that from a technical point of view, there are, but in your observation, were you actually seeing the capsules involving all 6 degrees of freedom? Because if there's any of them that you can assume away, you might be able to get it low enough that you could treat it in a more predictive manner.
Even if we managed to constrain the motion, like, so what we did when we dropped it is we tried to constrain the motion as much as possible to that plane. And even so, it's possible for the motion to be chaotic, and it's still highly sensitive to initial conditions. But yes, we are able to, like, we can possibly restrict some degrees of freedom by restricting the motion to like the plane, except when we do that, we see that sometimes it still doesn't work. Like sometimes it still bounces like towards and away from the camera. And it's just really hard to control that. Yeah.
Sure. I would just suggest that the degree of freedom when the capsule is rotating around the long axis could probably be ignored with fairly little effect.
Yeah.
Sure. Just as a comment for the reporter, in your earlier slide, you tried to show that the angular velocity of your wheel was slightly higher, I believe, than the angular velocity of your tic-tac as measured by your tracker. Just as a future reference, because as it's spinning like this, it's probably wobbling as well. And I don't know if your tracker can pick up the wobbling. So, because the wobbling is another axis of rotation. So you might want to put that in as well for your rotational kinetic energy calculation. Because there's no way your wheel will make the tic-tac rotate only purely in this direction, right? Your tic-tac is not a perfect capsule.
Yeah, all right, thanks.
Okay, are there any more questions from the jury? Seeing a general consensus of no. Okay, then we'll let everyone finish with the grading. And how should we let everyone know? Okay, so if you're done with your grading, I would appreciate it if you could just put it into the chat like I'm done. And then once everyone's done, we can go over the scores. Thank you. Okay, seems like pretty much everyone's done. Okay, so since there are so many jurors, I'll call out the name and then you can just tell me your partial grades and your final mark. And at the very end, we can do comments. Is that okay with all the jurors? Okay, awesome. So Daniela, Your
Okay.
reporter.
Yeah, 5.5 to 0.5.
Negative 0.5, right?
Uh-huh.
Okay, thank you. Carlos?
Yes, 6 to -1.
Thank you. Neil?
6, 3, -0.5.
Okay, thank you. Darby?
6, 2.25, -0.
Okay, yeah. And then Jesse?
6, 2, 0 for a total of 9.
Thank you. Kyle?
At 6.5, 2.5, and 0.
Okay, thank you. And Sheetal?
It's 5.5, 2, and 0.
Okay, thank you. Abdullah?
It's 6.5, 1.5, and 0.
Okay, thank you. And Michael?
7, 2, and -1.
Okay, thank you. Now for the opponents, Daniela?
Oh, yeah. 1.5, 2.5, 2.5, 0.5.
Okay, thank you. Carlos?
1, 3, 3, -1.
Thank you. Neil?
1, 3, 3.5 minus 0.5. Total of 8.
Thank you. Darby?
2, 3.25, 3 minus 1.5.
Okay, just for a quick pause, Andrew, can you confirm if we can have 0.25s in the system?
If you have 0.25, actually if you have like 2 decimals, round it. You can round it up or round it down, depending on what the juror wants. Only 1 decimal.
Okay, so for the opponents,
you can round them up.
Okay.
You can round mine up.
Okay, and then for the reporter as well. Okay, thank you.
Yes.
No irrational numbers, please.
Jesse?
For the opponent, 2, 3, 2, 0 for a total of 8.
Thank you. Kyle?
1.5, 2.5, 2, and -0.5.
Okay, thank you. Sheetal?
It's 1, 2.5, 2.5, and -0.5.
Thank you. Abdullah?
2, 3, 3, 0.5.
Thank you. Michael?
1, 3, 3, 0.
Thank you. Okay, now for the reviewer, Daniela?
1.5, 2, 1, 1, 0, 0.
Thank you. Carlos?
2, 1.5, 1.5, 1, +1, -1.
Sorry, 2, 1.5, 1.5, 1.
+1,
Yeah.
-1.
So for a total of 7, right?
Yeah.
Okay, thank you. Neil?
1, 2, 2.5, 1, 0, 0.
Thank you. Darby?
1.5, 1.8, 1.7, 0.8, -0.5, 0.
Thank you. Jesse?
1, 2, 2, 2, 1, 0 for a total of 9.
1, 2, 2, 2.
1, 0.
Okay, thank you. Kyle?
1.5, 2, 1.5, 2, 1.5, 1, 0, -0 for a total of 7.
Thank you. Sheetal?
It's 1, 1.5, 1.5, 1, 0, and 0.
Okay, thank you.
6.
Abdullah?
It's 1, 2, 2, 1, 0, 0.
Thank you. Michael?
1, 1, 2, 1, 0. Oh, did I miss one? 0 for last one.
Okay.
Yeah.
Thanks. Okay, so if we could have like the lowest and highest scores from each one, and if there's someone who wants to comment, we could also do that. So Danielle and Carlos, you both gave the lowest score for the reports. If you had any comments.
I can start. I want to say something that I really liked and something that I would have liked to see, right? Just to be fair. So I really liked that the reporter gave some type of statistical analysis, right? If you just stay at the level of looking at a single trajectory, then you can get the conclusion that, in my opinion, is wrong, that there's no much that you can do with it because just one trajectory is not enough, right? So I really like that you went like out of your way to do a lot of experiments and get more like statistics, right? I think that my only problem is that because of that, you didn't have enough time to bury the material, right? So it was a trade-off between the two of them, but it was pretty cool in any case.
Thank you. Kyle, you gave the highest mark. Could you comment on that, please?
Well, so I thought the experiment was very well done. And like Carlos was saying, the statistical analysis was very nice. And some kind of simulations, at least showing qualitatively that you get this kind of effect with higher bounces after some initial bounces. I thought the presentation was very nicely done. Yeah, I think pretty much across the board, I thought it was a great work.
Okay, thank you. Sorry, did I cut someone off for the reporter? Okay, cool. I thought I cut a juror off. Okay. So for the opponent, the lowest marks, there were a few of them. Sheetal, would you like to comment on your mark for the opponent?
Sure. So I mean, the 0.5 went away simply because he talked about energy, whereas like coefficient of restitution was at a time where certain moments of inertia also weren't calibrated. That's when this concept was sort of invented. So that was maybe why the 0.5 went off. Rest, I think a lot of the discussion should have been based on the assumptions, mainly because there was a lot of discussion of why this is chaotic and why couldn't we have a so a lot of the discussion that I thought should have gone towards the assumptions and maybe exploring those more as to why it is that you take a 2D assumption while at the same time you talk about degrees of freedom, and how do you have 3 rotational degrees of freedom in a sort of elongated object where typically we say that one of them is not as effective as the other two. And so yeah, I mean, I thought those were sort of missed points which could have been touched along a bit more. That being said, it was overall a good discussion, so I really enjoyed it and liked it.
Thank you. And Michael, would you like to comment on your opponent? You gave like the highest mark.
Oh, yeah. So I thought that the opponent brought up some really good points. I didn't know I'd have to comment, so I didn't write anything specific down. Sorry about that.
No problem. Okay, thank you. Sheetal, again, you gave like the lowest mark for the reviewer.
Oh, I mean, same thing as Michael. I didn't think I'd have to comment on that. It just overall seemed like more of a summary than an addition. What I was expecting is that the reviewer would go more on missed points because there were so many of them. At a point, I was feeling that they're just baiting us to ask certain questions because they know those answers, especially the opponent. So, I mean, I thought that the reviewer could have focused more on like just quickly summarizing it in like 30 seconds what they did, and focus more on what they didn't and bring that part out. So yeah.
Thank you. And the last one, Jesse, you gave the highest mark for your reviewer, a 9. Could you please comment on that?
Sure. I thought that the reviewer did a great job of doing an overview of what was said by the opposition and the reporter as well. The discussion analysis, I think, was really stand out. I think there was a good summary of like what of the points brought up by their opposition were relevant and which ones weren't relevant. So that's kind of my notes on that.
Okay, thank you. Is there anyone else who would like to comment before I submit these scores? No?
I don't want to comment on the scores, but just would the reporter like a general feedback? This was because something that we saw through, I think, all of the presentations, and a lot of the jurors brought this up. So, I mean, positive correlation has to be green, negative correlation has to be red. Like that's one thing that's I think a problem with the template itself. But we live in traffic lights world, so everyone wants to see green as positive and red as negative. So possibly that puts us off. And a second thing is, parameter is a sort of general term that is used for things that you mostly fix. And so what you want to talk about is something like dependent variables, independent variables, and then parameters. And then that doesn't sort of bait the question that what are you fixing, what are you varying? Because independence, what you vary, dependent is what you indirectly see the effect on, and parameters are things that you take as constraints into an account. So that. And I think another thing that I kept hearing was about parallax. So because your main thing is a linear measurement of height, maybe it's a good idea, so as to justify your 2D measurement, is just to take two perpendicular images, just move the same camera perpendicular and repeat the experiment to some degree of reproducibility. And what you can say is, okay, the deviations within our error bar, so it's as good as falling vertically straight. And if you all are curious, so about the coefficient of restitution, I think I can, I think you all can see the whiteboard. It would just be that your V relative is equal to your V plus omega cross R. So it's just this extra rotational thing that you all were talking about, rotational energy, which was this extra term. The moment you put that in, the formula basically becomes the same. So just out of curiosity, if anyone would like to know about this, that's what I was looking for. So, yeah.
Thank you. Okay, so that concludes stage 1, and I will submit the scores now. So let's take a short 5-minute break to stretch out before we start stage 2. And so we'll start stage 2 at 5:55. All right, thank you. Okay, if all the teams and jurors could just come back, that would be awesome. And from the teams, Upsilon, Anti-Quarks, and Sigma, please send me like in the chat, like who's going to be reporting from Team Upsilon, opposing from Team Anti-Quarks, and reviewing from Team Sigma. Thank you. Okay, Ellen from Team Anti-Quarks. Thank you. Reporter from Upsilon is Ali. Okay. And the reviewer from Team Sigma is Abe. Okay. Awesome. Okay. So we will begin now. I will submit these. Okay, and we will go to the timer and begin. Okay, so Team Upsilon, you have 5 minutes to get your presentation ready, but to save time, if you're done before that, feel free to start presenting. To all the jurors, if you could just like give a thumbs up, as Ms. Vanderkamp has suggested, to let us know that you're here, that would be awesome. Thank you.
Mic check, can you hear us?
Yes, we can hear you. Thank you.
Okay, I think we are ready to begin, so you can start the timer.
Okay, sure. Okay, so you may begin. The timer started, yeah.
Hello, everyone. I am Ali Elvi from Team Upsilon, and I will be presenting on problem D, spin drift. So the problem question is as follows. When a ring is said to roll in a parabolic bowl, interesting motion patterns may arise. Investigate the phenomenon. Sorry, my screen share window stopped.
Okay, I stopped the timer until you get it back on.
Sorry. Okay. So the most notable parameters that I covered in this presentation are how ring lengths and thickness change the anomaly, the effect of different drop angles on the ring movement, and how different levels of friction affect the phenomenon. Here's a brief overview of the slides, and now we'll move on to the experimental setup. So for my parabolic bowl, I initially used a metal bowl with a very steep curve. However, this bowl would often only result in the rings falling immediately. I also tested with a dinner plate with a very low curvature, which didn't result in the spin drift phenomenon occurring in the first place. I then decided to use this alternate bowl as it has a less severe slope. The bowl is a Beyblade Stadium, which was initially designed to be a parabolic bowl in which spinning tops are dropped. So it does fit our purpose. On the left, we have an image of the bowl with its dimensions, and on the right, we have a graph of the parabola that was made using the Desmos graphing software. Moving on to the rings, I mainly use keychain rings as they are solid and often perfectly circular. As we can see, the rings are many different sizes and have a variety of different thicknesses, all recorded on the slide. So these are the combined rings. These rings were made by essentially combining two of the rings that were previously mentioned by putting one inside one of the other. This allows us to increase the weight and thickness to see how that affects the phenomenon. This is non-stick cooking spray that is used to prevent food from getting stuck to pots and pans. I will be using this to change the friction levels of the bowl. I use this electrical tape to coat the bowl to increase the friction later into the experiment. And similar to the non-stick spray, I use this glue to coat the bowl to increase the friction significantly. So let's look at a few of the most common and most interesting patterns that are recorded. So this motion I will be calling ring falls. This is the most common motion that we see occur when trying to analyze spin drift. Instead of rolling around the bowl, the ring instantly falls onto its side due to gravity. This is rebound, which is the motion. This is rebound, which is the motion in which the ring appears to fall. However, it is going down at an angle. This results in one side of the ring hitting the bowl before the other. The ring then rotates along that side, absorbing the fall and losing a little energy. This motion often occurs in the middle of the bowl where the radius of curvature is at its lowest point. Slip and rebound. Another relatively common pattern is the slip and rebound motion. In this motion, the ring is sliding left and right while traversing across the bowl. When it reaches the end of the bowl, the ring rebounds due to its already sliding nature. Forward fall. Again, this motion is relatively simple as the ring rolls across the bowl and falls at the end. It is held upright due to static friction. 5. Rebound redirection. This motion is slightly more complex. As the ring is being dropped at a 45-degree angle, it has an increased torque. Therefore, after it's released, the ring falls, rebounds, and then switches directions. Of course, this is due to the torque. Forward, turn, and fall. In this motion, the ring covers the length of the bowl, and instead of falling instantly, it turns around and goes back before finally falling onto its side. Forward, turn, and rebound. This motion is similar to the previous motion, except the ring covers the length of the bowl, but instead of falling at the end, the ring rebounds and continues in the opposite direction. Flip-flop. This is the motion in which the ring appears to be rebounding multiple times before falling onto the face of the bowl. Wobble. Instead of going in a straight line, the ring wobbles left and right while covering the length of the bowl. This motion is similar to the rebound motion, but instead of falling and getting up, the ring's center of mass is being shifted back and forth from potential to kinetic. Forward and back. In this motion, the ring rolls to the end of the bowl and then rolls back in a straight uniform motion. The motion is caused by the static energy that is stopping the ring from falling over. Wobbling fall. The ring appears as though it's going to wobble across the bowl, but instead it simply falls. This is most likely due to the center of mass being too far one direction during the initial wobble. Figure 8. Okay, before I explain this motion, I just wanted to note I was only capable of achieving this motion using ring 6, which was the smallest ring. In this motion, the ring is going around in 2 connected circles. This is most likely due to changes in the mass distribution of the small ring while rolling. Semi-wobble. This pattern is similar to the wobble fall, but the wobbling here is less noticeable. Since I am using the combined rings, the difference between these motions is most likely due to the increase of weight and thickness of the ring. Wobble forward and back. Similar to the initial wobble motion, the ring slides left and right as it reaches the end of the bowl. However, in this motion, the ring also wobbles back while going down in a parabola. Wobble forward, back, and rebound. This is the last motion I will be mentioning, and it's the same as the one previously mentioned. However, instead of falling at the end, the ring rebounds and then falls. So now we will be moving on to the key parameters that I covered. Though I only showed around 15 motions, I dropped each of the 8 rings into the bowl a total of 30 times, making a total of 240 tests. For the first 15 recordings, I dropped the ring straight from the top of the bowl. For the following 15, I dropped the ring at a 45-degree angle. Here are some statements that can be made using the recorded information. First, we can say that ring 1, which was the ring that had the largest size, caused more dramatic rebounds. Also, this ring, majority of the time, would just fall over instead of rolling across the bowl. Ring 2, which was the ring that showed the most anomaly in its movement, was the best ring. It had many interesting movement patterns and rarely fell instantly. Ring 3, which was the same size as ring 2 but thinner, showed less variation in the movement, but still did roll better than ring 1. Ring 4, throughout the majority of the attempts, this ring would most often wobble and then rebound. Ring 5, this ring functioned similar to ring 4, but once again, less interesting movements occurred, which is interesting because ring 4 and ring 5 were the same size, except ring 5 had a greater thickness,
Ring 6 was the hardest ring to use due to its small size, and majority of the time this ring would just fall over. An interesting thing about ring 6 was that it was the only ring capable of making the figure 8 motion. Ring 7 and 8 were the two combined rings. They would often just fall over, but occasionally they wobbled back and forth. So what can we deduce using this information? So first, we can say for sure that if the ring is too large or too small, the phenomenon will be more difficult to achieve, which we can see by ring 1 and ring 6 being very difficult to manipulate. We can also say that the thinner rings created less interesting patterns than the thicker rings. However, if the ring is too thick, it will tend to fall over. When the ring is dropped at a 45-degree angle, the phenomenon is more likely to occur. And finally, if the ring is too heavy, it will wobble less. Next, we will look at how different levels of friction affect the phenomenon. For the following tests, I will only be using the gold ring as it proved to be the best at creating the phenomenon during the previous trials. First, I coated the bowl in a layer of rubber electric tape. This increased the level of friction and static energy. I then dropped the ring into the bowl 30 times. The main trend that I saw was that the rings would stand and roll for longer periods of time than when there was less friction. This is most likely due to static energy holding up the rings. Next, we have the oiled bowl. This was the bowl that was coated in the nonstick cooking oil. By covering this bowl with the spray, we significantly decreased the friction level. This resulted in the ring slipping and falling instantly on almost every trial. This is because the static force that is responsible for holding up the rings is significantly decreased. Finally, we have the bowl coated in glue. This bowl had a very high level of friction. When the ring was dropped into this bowl, it would reach near the middle of the bowl, freeze in place, and then fall. This is most likely due to a notable increase in static energy and a decrease in momentum. Essentially, static friction is the force that prevents the ring from immediately falling onto its side. When static friction is not present, like in the videos in which the bowl is coated in oil, the ring barely rolls. However, when static friction is too high, the ring movements are not anomalous whatsoever. To summarize, without the proper level of static friction present, the phenomenon will not occur. To conclude, here are the statements that can be made regarding spindrift. First, regarding the ring, if the ring is too thin, the odd motions will occur more rarely. If the ring is too thick, it will often fall onto its side. If the ring is too heavy, it will wobble much less. If the ring is too large or too small, it will be more difficult to create the phenomenon. The optimal ring is thus found by experimenting with a variety of rings of different weights, sizes, and thicknesses. In my case, this was ring 2. Moving on to the bowl, if the friction levels are too low, the ring will slip and fall. If the friction levels are too high, the ring will follow a straight path and then fall. If the friction level is optimal, the ring will roll for longer periods of time. If the bowl curvature is too high, the ring will most often crash at the bottom due to the increased velocity. If the bowl is not adequately curved, the phenomenon will not occur whatsoever. The ideal bowl thus has a medium level of friction. In my tests, the bowl coated with the rubber tape had the best results. Thank you for listening to my presentation. That was Ali Alvi recording on spindrift.
Thank you. 2 minutes for opposition questions.
Do you have any experimental data or quantitative data for your?
No, I chose not to record data because the motions are rather chaotic.
Oh, okay. So did you investigate further into this chaoticness of the phenomenon?
Yes, I recorded a lot of the more chaotic motions and looked at it from a different perspective on why they occurred.
Did you release all the rings by hand when you were doing?
Yes, I did, but I didn't release them from varying heights. I released them on the edge of the bowl.
Okay. Because of that, do you believe your experimental setup is actually repeatable?
It is
for your multiple trials.
I believe it is mainly because I didn't drop the ring from varying speeds and different velocities or different heights. I simply aligned it with the edge of the bowl and simply just let go.
Okay. How do you determine that your bowl is actually parabolic?
So what I did is if I can go back to the slide. Oh, that's fine. So as I had a graph out of the parabola, and I got that by measuring various points on the bowl to see which ones, to make sure it was a parabola.
Oh, okay. So did you consider the bumps or the cracks in your bowl that you have?
No, because there were no noticeable bumps or cracks.
Oh, okay. Can you go to slide 26? Is your camera in that slide held by your hand when you were filming it?
1 minute, please. This one?
Yes. Is it by
Yes,
your?
it was.
Oh, do you believe that's stable and gives the correct view that you need?
Short answer,
Yeah,
please.
because, yeah, I think it's fine because I'm still getting the entire bowl and it's not that significant of a movement.
Okay, thank you. 3 minutes for preparation of the opponent. Please share your screen so you can start now.
Okay, I'm sharing my screen. Give me 2 seconds.
So I'll just repeat myself in the future, like for all the teams, please share your screen before the timer is up. Thank you. Okay, please begin. The timer started.
Oh, sorry. Hi, my name is I was muted. Sorry. Hi, my name is Ellen Wang, and I'm from Team Anti-Quarks, and today we'll be opposing the problem of spin drift, specifically what happens when a ring is set to roll in a parabolic bowl and the interesting motion patterns that may arise. So firstly, a couple tasks that we must go over to complete this problem statement is to reproduce the phenomenon successfully. And to do that, we need to construct a repeatable experimental setup. We also need to qualitatively explain the phenomenon and also investigate the effects of the key parameters to the phenomenon along with some theory to back it up. So the summary of the opponent's report and what they discussed the different types of motions that may arise from releasing different types of rings onto different types of bowls. They also discussed the different trials and their specific outcomes, as well finally the impact of friction through their presentation. Some merit is that they did reproduce the phenomenon successfully with a bowl and a ring, and they also did identify different motion patterns that may have arisen from using, for example, different rings or different friction coefficients. Some possible next steps that they can improve on is that they have a lack of theory. So they don't have any predictions using theory of what will happen to the ring. They don't have any predictions with the equation of motions, and they also did not back up the chaoticness of this phenomenon with theory as well. They did not effectively investigate the effect of the key parameters on the phenomenon using theory. They didn't graph. They have lack of graphs, and as well as a lack of equations to also back up their experimental findings. They do also miss some key parameters such as initial velocity, the ring curvature, and they could also investigate key parameters such as the moment of inertia, which they did not include in their presentation. They didn't have any experimental data that was graphed and plotted in comparison to any theory that they produced. They only showed videos of their experiment. They did not take any data and record it. And furthermore, their experimental setup was uncontrolled because, first of all, the keychain rings are not smooth. The rings have bumps on them. They're keychains. The bowl that they used as well has cracks, and they, with the bumps that was in the bowl, they also furthermore put tape on top of it for friction purposes, and they also put oil on top of it, which both the tape and oil can. How did you ensure that it was actually smooth, and it didn't cause any effects on the phenomenon? Thirdly, their release mechanism was also uncontrolled, as it was with your hands. There are better release mechanisms that we can use that actually controls the phenomenon to ensure that you're not adding any initial velocity. As well, the camera angle does not film from for example, a parallel view to the bowl. So the camera angle is also used by your hands, which hands are unstable compared to other things we could use to stabilize the camera. To give an overview of our discussion, firstly, we'll be talking about the lacking of theory and experimental verification in the presentation, as well as discussing how to further improve their experimental setup so they can create more repeatable trials. Thirdly, a chaos discussion using Lyapunov exponent, for example, to discuss and prove that's actually chaotic.
Okay. Thank you. And now the discussion may begin.
To begin, how would you characterize the shape of your ring, including how to calculate the moment of inertia?
Sorry, the ring, how I describe the shape?
Yeah, describe the shape of the ring.
Circular?
So how would you calculate the moment of inertia in that case?
I didn't take moment of inertia into consideration.
And also circular is 2 degrees. The ring is a 3-dimensional shape. So circular.
Okay, then like a curved cylinder.
Did you verify this using, because the keychain rings seem to have like irregular shapes?
It may seem like that, but I did sand down the keychain rings prior to releasing them, which is why they weren't rough, and I didn't take that into consideration.
Could you screen share the ring that you used?
Sure. Just give me a minute.
And also, how many degrees of freedom do you think your ring would have? in the meantime when you're sharing the screen?
5, I believe.
5. Could you explain 5? Yeah, so the rings have dents in them. They're not the shape that you described them to be because of circular dents. And it's extremely difficult to calculate the moment of inertia in that case. And because the phenomenon does deal with the moment of inertia quite a lot. And also you said that your phenomenon was chaotic. How would you verify that it was chaotic? Did you have any graphs or any theory to back that up?
As to why they are chaotic?
Yeah.
Not all of them are chaotic. A lot of them are, but not all of them, which is why I couldn't make a stable conclusion. Because some of them, that's like when the ring goes back and forth, that's a uniform motion.
There is actually a way to verify that it is chaotic. How we verified it was a suggestion that you could use to how you verify it would be to use the Lyapunov exponent, which is an exponent that if it's positive, that it does it does show that the phenomenon is chaotic. So if you use the Lyapunov exponent, and I can show you the equation of it.
Yeah, but it's really sensitive to the initial conditions.
Which means that being sensitive to initial conditions does mean the phenomenon is chaotic.
Yeah.
So you can use the Lyapunov exponent as theory to back that up, because just observing that it's chaotic it's not enough theory to back it up.
Okay.
I'll screen share and I will write the equation down to show you.
Wait, can you just use the whiteboard?
Oh, sure. So wait a second. So for the Lyapunov exponent,
Here, I will open up a whiteboard. So pause the timer and open up a whiteboard for you too. Here you go.
So the Lyapunov exponent is a function, which is, I can't annotate it.
I can't see anything.
Yeah.
Cannot see anything either.
Okay, so for the Lyapunov exponent, it's a function, which is the deviation between trials in respect to time, and it equals the initial deviation. Initial deviation equals the initial deviation times e to the power of the Lyapunov exponent times t, which is time. So if you can prove that.
Are you writing something?
Yes, I'm writing something.
I don't think I'm seeing it.
Oh.
Sorry, is that just me?
I cannot see it either. Please pause the timer.
Oh, okay. Sorry.
Yeah, I also cannot see it.
Okay, I will reshare that then. Okay. Can everyone see this?
Nothing showing up yet. Okay, now we can see it.
Okay. So as I was saying, if you can find that this value is positive, then you can prove that the phenomenon is chaotic. And if it isn't chaotic, then there should be equations of motions that can predict the trajectory of the phenomenon, the ring.
Yeah, I agree.
Okay. And also, sorry. So as well, your experimental setup, when you place the camera in an angle that isn't, for example, parallel to the bow, there may be like variations or like not precise tracking of the ring, and that could cause some like false.
Sorry, can you elaborate on that?
because we didn't track your experimental data because you didn't track it. So because you didn't track it, like there's no graph to back up any of your conclusions of the of your predictions. And even if you did track it, because the camera isn't in parallel, it wouldn't have been accurate anyway. And also you said that sometimes it wasn't chaotic. So could you write down do you have an equation of motion to predict it? If not.
No, when I'm saying it's not chaotic, it just the ring is rolling back and forth. There's no strange motion.
So there should be an equation of motion to predict it. So an equation of motion that could be used to predict especially the initial part of the phenomenon is you could give me 2 seconds. One of the equations that you could use to predict is a Lagrangian equation. And after finding the Lagrangian equation, you can also take the derivative to produce an Euler-Lagrange equation. And using that, you can determine an equation according to acceleration, which is x double dot, which is acceleration equals negative 4k squared. K is the stretch of the parabola. So also, if you have the parabola to the power of 2, x dot to the power of 2, x to the power of 2, x plus 2, g k x over 1 plus 4k squared. So that's an equation of motion that could be used to predict especially the initial trajectory of the ring, because it does just roll down the bowl, and that initial trajectory is predictable. So that's an equation of motion that could be used to do that. Furthermore, you didn't really first of all, you said that you dropped the ring down into the bowl 3 times, but do you think that 3 times is really enough to conclude to your conclusions of the motions?
That's not correct. In total, I dropped each ring not equally in amount of times. I did 15 drops straight, 15 drops from an angle. So 30 drops, but 30 drops for each ring, and there are 8 rings. So I dropped the ring a total of 240 times. Not 30.
Oh, okay. Okay. Can you screen share and qualitatively explain actually why it flips, like why the ring flips?
Sorry, which slide are you referring to?
Like, can you qualitatively explain why the ring flips and why?
Which?
Like, for example, when the ring is in the bowl and it rolls down, and for example, once it gets here, it starts to flip, as in this angle. The tilt, it starts to tilt like it starts to tilt this way and it starts to flip this way. So for example, the reason why that actually happens is because when the ring is rolling down the bowl, that there are many forces acting upon it. So some forces dissipate the energy. So when it rolls down the bowl, the energy starts to dissipate and eventually starts to tilt because it doesn't have enough torque to keep it spinning. And once it starts to tilt, it falls. But however, there's gravity because the bowl is parabolic. So the gravity instead like causes it to roll down, and then it gains velocity again, which is why it can keep rolling. However, and that's another reason that's the reason why you can vary like the bowl curvature, for example, to get different to see the impact of it. And once you, for example, the ring loses enough energy and it starts oscillating in the middle, that also is part of the phenomenon. Something that you didn't discuss is that it often oscillates in the middle.
An event,
Oh, it just keeps oscillating in the center of the bowl, and that's due to like the potential and the kinetic energy that's happening, because when the ring is, for example, tilted this way, here, let me draw it. When the ring is tilted like this part, sorry. When the ring is tilted like this part has high potential energy and this part has kinetic energy, and when it drops, the potential energy turns into kinetic energy, and that's why it starts to oscillate.
Okay, thank you. That's the end of the discussion. 1 minute for the opponent to summarize. The opponent? Anti-Quarks?
Ellen?
Sorry, I'm sharing my screen. To conclude our opposition, the opposing team had a lack of theory, and the theory that could have been included is, for example, equations of motions that could have predicted the motion when it was predictable, and we proposed that the opponent can also use Lyapunov exponent to prove why it is chaotic and explain and use that to prove that it is actually chaotic, and if the Lyapunov exponent is positive, then that could be proved. And we also discussed how there was an unreproducible, not reproducible experimental setup. The ring was released by a hand, which was not repeatable, and also the ring has bumps, and so does the bowl. As well, the moment of inertia was not mentioned throughout the presentation much, and that could have been carried along with other parameters.
Thank you. 3 minutes for questions from the reviewer.
All right, so this is to the reporter. Do you think that what do you think is the relationship between interestingness of the behavior and the curvature of the bowl?
Okay, so in my experience, the curvature, when there's more curvature, there's more interesting in motion. However, when there's too much curvature, it just goes too high of a speed and falls onto its side. However, when there's no curvature, like as I said, I tested this using a dinner plate. I rolled the ring and nothing interesting occurred.
To the opponent, what do you think of this?
For the dinner plate, the dinner plate is not a parabolic bowl, so that wouldn't be part of the.
Okay, thank you. I agree with the qualitative trends that the reporter found, but I would disagree with the mechanism. I believe that an overly curved bowl is not interesting because it would hit the edge of the bowl. So another one, to the opponent, what do you think is the most important parameter that the reporter did not vary in their experiment?
The most important parameter that they didn't mention in their experiment as much is the moment of inertia, because it is a spinning and rolling ring. So the moment of inertia is pretty important, and it can also affect how long it rolls for.
All right, so seeing as you believe it's that important, what do you think would be the dependence of the interestingness of the behavior on the moment of inertia of the ring?
For the moment of inertia of the ring, what we discovered is that it affects the motion pattern, first of all, because the moment of inertia makes the ring more stable. And when it's more stable, it's less reactive to the forces in the bowl. So it can also roll for longer before it topbles and falls in the center of the bowl. And as well, if the moment of inertia is way too small, it doesn't do all the flipping and it doesn't display the interesting motion, which is why we made a point to make the ring slightly larger and have a larger moment of inertia.
All right, thank you. To the opponent as well, you mentioned that the bowl has cracks. To the reporter, what do you want to say about this? Reporter?
Oh, sorry. I'm not sure what cracks she's referring to, because last time I checked, the bowl was smooth. If she's referring to the cracks in between the rolls of tape, those are not very significant, and there was no real way of not having them, because either the tape overlapped or there were slight gaps. I prefer the gaps because if there was a change of height, it would be more problematic than a decrease in height.
But opponent, you seem to disagree with this, so why would you think that?
Because when I...
No, to the opponent.
When I was referring to cracks, I may have used the wrong word. I meant the ridges in the bowls. In the plate that they use with the red one, there was like ridges going down. And if we want, you can have the reporter can show the slide again. With the ridges.
To the opponent, do you think would be a good way to find out if the parabola was a parabola? If the bowl was a parabola?
What we did was you can also like track the cross-sectional area of the bowl if we wanted to determine if it was parabolic, and also.
Thank you. Okay, 2 minutes for the preparation of the reviewer. Okay, Team Sigma, you may begin.
Hello, I'm Abe1, and I'm going to be reviewing problem D, spin drift. When a ring is set to roll in a parabolic bowl, interesting motion patterns may arise. Investigate this phenomenon. So we identified 4 tasks. We have to find a satisfactory definition of interesting. So we know that what we're talking about is something that everybody agrees on. We have to qualitatively describe the motion patterns, then quantitatively describe them, and identify the effects of relevant parameters. So we found that the report had a limited fulfillment of these goals. There was in the theoretical analysis, there was a good qualitative description of the various things and identifying the patterns. And in the experimental confirmation, there was certainly a very copious amount, an excellent copious amount of qualitative video analysis and cataloging of those various videos into different modes. And we found that these modes are very important for analyzing the behavior of complicated systems like chaotic systems. So that was a good qualitative move. On this, so we found like the merits of the report were generally around the qualitative behavior and looking at, they varied a number of the parameters such as changing the rings, and they also varied the parameters of the bowl, though that might have been extended by changing the physical size of the bowl itself. There was good qualitative categorization of the motion patterns and good parameter analysis. However, there was a lack of quantitative analysis, and there was, as I identified earlier, a lack of identification of the interesting behavior. So let's just take a look. The opponent was generally focused on 2 main things. They highlighted repeatable and controllable experimental setups, and they also emphasized the importance of quantitative theory and quantitative data and equations in their analysis. So generally speaking, he did get to the heart of the weaknesses of the reporter's presentation, this lack of theory and the lack of quantitative verification. However, they might have focused a little bit too much on this lack of numerical analysis, seeing as their job is to interact with the presentation that the reporter has given us. And despite its weaknesses, we must interact with it on the level that it is made, which is the qualitative level. Another thing that I'll get to later is they largely confuse the conception of understanding something to being able to model it quantitatively. When the reporter was able to understand a principle, but the opponent felt like the reporter wasn't able to look at it quantitatively, they felt like the reporter didn't understand it. I feel like this was a misunderstanding by the opponent. So let's take a look at the various things that they discussed over the course of the discussion. First off was the control of the initial conditions. So I actually disagree with both of the points made. So on the quantitative side, I think that the point raised by the opponent is not important. This is because we're just looking for a tangent vector in phase space. We have a ring at a certain position and we have the derivatives of its position. And we want to find what the acceleration is so we can quantifiably model it. How it got to that point in space does not matter because it's not going to have memory because it's a very simple dynamical system. On the other hand, qualitative analysis doesn't really depend on small variations in the initial parameters. On the degrees of freedom side, I agree with the reporter's response. However, they might have been able to analyze non-holomorphic conditions that restrict phase-space dimension. On the side of chaos, I believe that the reporter demonstrated an adequate understanding of the principle of chaos in their system, and that the opponent identified that they weren't able to look at it quantitatively, but I don't think that this was a serious impediment to understanding. For the theoretical analysis, I believe that sure, yes, this was a weakness in the reporter and the opponent did a good job of analyzing this, but perhaps they spent too much time focusing on this. For the qualitative behavior, this is like a quantitative behavior. So let's take a look at the MIST physics. In the MIST physics, there was a complete lack of any kind of aesthetic system for looking at what is interesting behavior. There was also no analysis of the slip versus no slip condition, which can lead to different kinds of behavior. And there was no variation of the bowl size or quantitative work. And generally, there could have been an extension to the experimental work. Thank you for listening. Abe Wine, spin drift.
Thank you. 2 minutes for concluding remarks from the reporter.
Okay, hello, once again, Ali Alvi. So I do agree with the opponent that I do have a lack of quantitative data. However, I tried to make up with this as best as I could with qualitative because, to be completely honest, I was focusing more at a qualitative approach because it's a very interesting problem due to the odd motions of the rings. Furthermore, I don't agree with the fact that the experimental setup had cracks in it because I did record prior to it to make sure it was a parabola from taking multiple points along. And I also regarding the roughness of the rings, I sanded down the rings prior to their release. Furthermore, regarding the release point of the ring and the ridge that the opponent was referring to, the ridge was behind the point of release for the rings. So I angled the ring at release over the ridge. So the ridge did not affect the experiment whatsoever. And then regarding the cracks between the tape, these cracks were very small, barely affecting the overall motion of the rig. And regarding the opponent mentioning that one of the questions the opponent asked regarding a qualitative response of one of the questions, I was not provided with a moment to explain this, and I believe I could have. And over my presentation, I explained from a qualitative standpoint why this occurs and a variety of different patterns that I recorded along the way. And I believe that that was adequate for my experiment.
Okay, thank you. Questions from the jury?
I can start off with a question for the reporter. So in one of your slides, when the ring patterns, you talk about one of the motions being forward and back. You said that the reason why the ring is kept upright is because of static energy. Could you explain what is static energy again?
Yeah, so static friction is what I said was responsible for keeping the ring upright. So essentially, static friction is the force that prevents the ring from immediately falling onto its side, because as we see in the two experiments with the glue and the oil, when static friction was not present, the ring immediately fell, and when static friction was over present, the ring was just sticking to the bowl. Does that answer your question?
Okay, sure, thanks.
Sorry, I have a question for the reviewer. So you mentioned what is a holomorphic constraint?
A holomorphic constraint is a constraint where the amount of degrees of freedom of the position of the object is the same as the amount of degrees of freedom of the way that the object can move. For instance, the no-slip condition imposes a restriction on how the ring can move once it's got to a certain position, so it's a non-holomorphic constraint because it reduces the amount of degrees of freedom for how the ring can move. The way this looks qualitatively is the ring doesn't just fall down because it has to obey this restriction in how it can move.
And what's the difference between that and a holonomic constraint?
Sorry, holonomic, that's right, that's the word. I was confusing it with the other one.
Okay. Don't worry about it, that gives me mental peace. I just wanted to check that, that it was just like a typo.
A holonomic constraint is one where they have the same dimension. Like if you have 6 degrees of freedom of where you can be, then you got 6 degrees of freedom of where you can move. You can like move in any direction in the global phase space.
Okay, thank you.
Thank you.
For the opponent, Ellen, you raised the issue of Lyapunov stability constant. Just to clarify, is having lambda greater than 0, is that a necessary or a sufficient condition for you to declare it's chaotic?
That exponent more just shows the deviation between the trials with the same conditions. So it just shows that they deviate, so they don't so they're really sensitive to initial conditions. So it shows.
Okay. So in that case, just because it's positive doesn't mean you can, declare it right away. The thing is, what do you expect the reporter to measure? You had something times e to the lambda times something else. What do you expect them to measure?
I would say that you can measure the deviation because you need the deviation between trials. So you can have 2 trials, for example. You measure the deviation between the 2 trials, and there are difference between displacements. For using the difference between displacements, you can track that, and then from the deviation between the locations of the ring at the same time, and then you can track that. And what we did was we plotted it against. So we calculated the Lyapunov exponent for each time, every single time, and it was a function. And then we can see that in the beginning it was negative, however it became positive as the ring started to roll. So that showed that it was. Yeah.
So you measured spatial distance between the 2 of them?
Yeah, the XY position.
Okay.
So I have a question for the reporter. So you showed some like coefficients on an equation for the parabola of your Beyblade dome. Where do those coefficients come from again? Could you explain how you took those measurements?
Okay, so what I essentially did is first I ensured that the circumference of the bowl was circular so that it was a circle, and then I took the length, and then I took the deepest point of the parabola, and then I graphed it out. And then along the way, just to ensure further that it was a parabola, I checked points that were on the bowl in between the deepest point and the side of the bowl to ensure that it was following along the graph, and they did correspond.
And how many of those points did you take along the curve?
So I took 4.
Okay, thank you.
I have
can I
one
ask
more question.
Oh.
There is time, but I don't know.
Yeah, definitely. Ask ahead.
Okay, so last thing. For all of them, for all of you, sorry. What's the importance of the ball being parabolic? What happens if it's spherical? I don't know, or another shape, right?
I would love to answer. I spent a lot of time talking about this in my report. So basically, I found that there's like, so you know how it's a differentiable curve? So there's like a plane that kisses each point. So then you can find the deviation from this local linear plane. And actually, it turns out that the deviation is only a function of like the radius of the area that you consider. And it's not a function of where on the bowl you take this point. So that's an interesting property of the parabola, kind of because it's like the second derivative is constant. In addition to this, I also did something where I investigated the curvature of a parabola, like the kappa, the 1 over the radius of curvature of the point. And then I found that among the family of functions that have the absolute value of x to an exponent, the parabola is the only one that has a well-behaved curvature. The ones that had a lower exponent, the curvature tended to infinity, which meant that at the vertex, no ring of any size would be able to fit and roll continuously. And that would be bad for those other kinds of bowls. So those are some special aspects of the parabola that I found.
Thank you. If anyone has something to add, but I'm happy with the answer.
Okay, if that's everything, then are there any more questions?
I have one more question. Is that okay?
Yep, sure.
Okay, to the reviewer, you mentioned for the case when the bowl is overly curved, it won't be interesting because the ring would hit the edge of the bowl. What do you mean by that?
Oh, interestingly, now that I have talked about my little spiel about the curvature, if the bowl is too curved, then the curvature gets much higher, which means that you would need a very small ring in order to fit and roll continuously inside of this bowl. And so if we could just consider keeping the ring the same size and then increasing the curvature of the bowl, intuitively, like if you try to put the ring in there, it's going to discontinuously just like hit 2 points of the bowl and it's not going to be able to roll continuously. So if we make the curvature too high, it's not going to be able to roll continuously. And so it's going to like hit the edge, it's going to lose energy due to like collisions, etc. And it's not going to be as interesting of a motion pattern.
Okay, thanks.
Are there any more questions? Okay, then once again, whenever all the jurors are done marking, just type done in the chat. And once the majority of people are done, then we'll enter scores. Thank you. Okay, it seems like most people are done. And if you're not done, we'll just come back later. So for the reporter, Danielle, can you announce your partials?
2, 1.5, 0.
Thank you. Carlos?
Yep, give me a second because I closed the PDF. Sorry about that. Okay, so for the reporter, right?
Yep.
4, 1.5, -1.
Okay, thank you. Neil?
4, 2, -0.5.
Okay, thank you. Darby?
5, 2, -0.
Okay, thank you. Jesse?
5, 2, -0 for a total of 8.
Thank you. Kyle?
2.5, 1.5, -0, total of 5.
Thank you. Sheetal?
5, 1.5, and 0. So that should be 7.5.
Yep, thank you. Abdullah?
3, 1.5, and 0.
Thank you. And Michael?
5, 1, and -1 for a total of 6.
Thank you. Okay, for the opponent, Daniela?
I have 2, 3, and 1.5. 0.
Thank you. Carlos?
1.5, 3, 2, 0.
Thank you. Neil?
1.5, 4, 2.50 for a total of 9.
Thank you. Darby?
1.6, 2.7, 2.5, -0.3.
Thank you. Andrew, there's a problem to fix with rational numbers, but okay. Jesse?
1, 3, 2, 0 for a total of 7.
Thank you. Kyle?
1.5, 3, 1, -0, so 6.5.
Thank you. Sheetal?
1, 2.5, 2.5, and 0. So a total of 7.
Thank you. Abdullah?
2, 3, 2.50.
Thank you. And Michael?
1, 4, 2, 0 for a total of 8.
Thank you. Okay, for the reviewer, Daniela?
I have 1.5, 2, 1.5, 1, +1, and 0.
Thank you. Carlos?
1.5, 2, 2, 1.5, +1. 0.
Thank you. Total of 9, right, Carlos? Yeah, okay. Neil? You're muted, Neil.
Sorry. Okay, 2, 3, 3, +0.5, +0.50 for a total of 10.
Thank you. Darby?
Mine exceeds 10. Do I need to fix it? Or do you
No,
guys-
I think it's okay, actually. The system
Okay.
is going to account for it.
Okay, so I have 2, 3, 2.5, 2, 1, 0.
Thank you. Ooh, that's really high. Okay. Didn't expect the system to account that, but I think it should be okay. Jesse?
I got 2, 2, 2, 1, 1, 0 for a total of 9.
Thank you. Kyle?
1.5, 2, 2, 1.5.
Sorry,
plus
1.5. What's the second
2,
one? 2. Yeah.
And then 2, 1.5, +1, -0, 9.
Thank you. Sheetal?
It's 1, 2, 2.5, 1.5, 0.5, and 0 to a total of 8.5.
Thank you. Abdullah?
1, 2, 2, 1, 1, 0.
Thank you.
Yeah.
And Michael?
1, 3, 3, 2, 0, 0 for a total of 10.
Thank you. Okay. Just in the interest of time, because I'm sure everyone is getting tired, if there are any jurors who would like to comment, feel free to comment, and then right away we'll get started with the third stage.
I feel like I should comment for my astronomical reviewer mark. I just felt like there was nothing that I would change about the way that the reviewer handled that role this round. I was very, very impressed, especially with the how synthesized and condensed their reviews of both the report and the opposition were. I felt like they covered every question that came to my mind during the presentations, and that they did so in a way that was in a positive, sportsmanlike manner. And I was just thoroughly convinced by everything that they said.
Thank you very much.
I have one quick feedback for the reporter. For the discussion, it seemed like the opponent was asking you questions. You're allowed to ask questions back. That's it.
For the reporter, one thing that everyone pointed out, which is something you could have used to your advantage, was that it said interesting. It never said quantify, qualify. So if you had just spent a slide saying that the most interesting thing is to look at it because the visual fields are the most interesting thing happening there, I'm sure everyone would have given you at least 2 more marks just for putting that one thing there that is interesting. This is the most interesting thing happening. So I mean, you could rather justify your focus rather than change your focus. Because personally for me, that focus is pretty much like the most interesting thing. And I was just looking at your videos, like honest justification, like honest disclosure. And if you just justified it, it would have been almost a perfect thing.
Yes,
Thank
the
you.
observer is the most interesting thing.
That's some really useful feedback. Thank you.
I have a quick feedback for the opponent actually. So someone already mentioned it, that there was a lot of focus on the lack of theory and quantitative data in the reporter's presentation, and I agree with this point. But I think that it's like, if you're in a discussion, even if that's true, it's important to be able to still have a discussion, right? And so what for example, one of my bring it upstairs to the level of theory by talking about Lagrangian and all this stuff. But to be very fair, you could have forgotten about the theory and just discuss what you were seeing in those movies, right? So I think it's important to keep it always at the level where every party can actually have and participate in the discussion.
Right? I'll just quickly say that I think the easiest way to kind of tick the theory box would be to fully describe a two-dimensional toy model. I think that this would create a good leaping off point for going into the discussion of the 3 dimensions. And I think you could just say, look, it's a chaotic system. There's no real point in trying to build a fully fleshed out 3-dimensional model, because it's not going to be analytically predictable, or something like that would tick that box for me.
I just wanted to emphasize that I also appreciated the reporter's approach to this problem, because I also felt like the interesting part left it open to kind of either a kind of quantitative designed experiment where you're testing the dependence on certain parameters, whereas I feel like this reporter took advantage of the possibility of doing observational experiments. And so I thought that was kind of brave relative to the other experiments going on that I've seen. And I was also impressed with the reporter.
Thank you to all the comments. If there are no more comments or feedback, then let's take a short 3-minute break and then get started right away so we can get through this last stage. I apologize for any background music that's happening. It's completely out of my control. In the meantime, can the 3 teams please just send who's doing the roll? Thank you.
Dave, can you just confirm? I believe it has to be 3 different people doing the jobs of reporting, opposing, and reviewer.
Yes, it has to be 3 different people.
Yes. So Aaron, is that the one who was just on, or was that Ellen?
That was Ellen. That was just
Oh,
on.
okay. Sorry, my apologies.
Okay, so if all the teams and jurors could just come back, that would be awesome. And just give a thumbs up if you're back and ready to begin.
I see someone's practicing scales.
Yep, that's right under me. The walls are really thin here.
Okay.
Okay, awesome. So let's get started. Okay. So Team Anti-Quarks, you have 5 minutes to get your presentation ready and prepped. But in the interest of time, if you set up earlier, feel free to get started. Okay, the 12-minute timer has started. Please begin. Anti-Quarks?
My teammate says she is having problems unmuting herself.
Okay.
Hello?
Oh, we can hear you. You're just really quiet.
Oh, wait. Excuse me. All right. I'm gonna.
Can everyone hear the reporter?
Hello? Hello?
I see some thumbs up. Okay, yeah, like Aaron, we can hear you. You're just quiet, barely. Okay. Is there any way, Aaron, that you can turn up your mic?
I'm using earbuds. I'm not sure how to turn this up.
Maybe just put them closer to your mouth.
Like this?
Yeah, that's much better.
Oh God. Okay. All right. So I'm ready whenever.
Okay, you can begin, and I'll start it like after 20 seconds have passed. So just start.
All right. Hello. My name is Aaron Zhang, and I'm from Anti-Quarks, and I'll be presenting problem number C, B dynamics. So this problem states that a circular hoop rotates about a vertical diameter, and a small bead is allowed to roll in a groove on the inside of the hoop. Investigate the relevant parameters affecting the dynamics of the bead. So the parameters that we decided to vary that we thought would have an effect on the dynamics of the bead is one, the angular velocity, which is the speed at which the hoop spins at, the radius of the hoop, the coefficient between the friction coefficient between the bead and the hoop, the tilt at which the system is put at, and as well as the mass of the bead. Here is an overview of the presentation. We're going to have an introduction, which is a reproduction of the phenomenon.
Sorry, Aaron, can you get closer to it again? I think you just got really far again.
Sorry. And then we're going to go through an experimental setup. And then we're going to go through theoretical model, followed by key parameter interactions, and finally a conclusion. So here is a replication of the phenomena again. This view was taken from above. It could be seen that the bead is metallic and there are measurement labels on the side of the hoop, each distance 1 centimeter apart, just for tracking and calibration purposes. And here's the experimental setup. But first, for our angle measurements, we used tracker. So basically, we used an iPhone to take the photo, to record a video of the hoop spinning from the front side view, and then we just put it into tracker and selected the frame at which the hoop is facing directly towards the camera, and we measured the angle using just using the angle tool. And then for experimental measurements, for the we measured the diameter of the hoops. We had several different hoops, and we measured the diameter using a measuring tape, and these are the measurements that we got. We had 6 up to like 7 different hoops. And then as well for the mass of the bead, we used a digital scale, and as well as for the diameter of the bead, which is relatively small, we used a caliper. So both of these would ensure accurate, precise measurements. And these are the measurements that we got. And finally, for the rest of the experimental measurement, for video measurements, we used the tracker's ruler tool. After calibrating it in tracker, we just basically used the ruler tool to measure out the length that we needed, and as well as we used a protractor, as mentioned before, to measure any angles. And then here is the experimental setup. The whole system was put in front of a black screen so that when put into tracker, there is a difference between the metallic bead and its background so that we could use auto tracker to accurately track it instead of manually, which could cause some measurement errors. So we have the hoop, and on top of it, we zip tied a GoPro Gen 4 to it. And then we had 2 light sources on the side, and as well as a DC power supply which is linked up to a stepping motor, which would spin the hoop around, and we are able to vary the angular velocity using that DC power supply.
Aaron, can you get closer again? Sorry.
I'm sorry, I'm literally up next to the mic. And next we're going to talk about our theoretical model. We're going to start with qualitative account, which is basically how the system works and how the bead is able to stay at an angle, and as well as the angular velocity to back up the angular velocity. So here's the geometry. So from the front view, we were able to see the hoop spinning, and the diameter is shown there. The angular velocity at which the hoop spins at is known as W squared. And then the equilibrium angle will be just theta, and then the radius of the hoop is known as R rho. So now how does the bead climb and stay at a certain equilibrium angle after depending on So there are 3 different stages during this phenomenon. Stage 1, which is when the bead is not moving, so the hoop is also not moving. So the system is just in rest position, and during this time, there are 2 forces acting upon it. There's a natural force and the gravity force. And then stage two is when the bead is climbing up the hoop, and during this time, if you refer to the diagram on the middle bottom, the different forces acting on it is gravitational force. There's also friction, and then Fc is the centrifugal force, which is also the same as the angular velocity, and as well the normal force perpendicular from its surface. And then stage 3 is when the bead is in equilibrium, which is basically when it seems like that it's stuck on the side of the hoop. This is when all of the forces basically cancel out, and friction is countering gravity, which is partially how it's keeping the bead up and making it seem like it's stuck. So that's when all the forces cancel, and so as the velocity increases, the bead begins to float in free space, and the system becomes centrifugal, and this is when the object begins to move as far away from the center of the axis as possible. And back in stage 3.
Aaron, I'll pause the timer for a sec. Like you were in a position where we could actually hear you at one point, and then you moved, and then we can't hear you much anymore.
I'm sorry, Dave. Like the mic is literally right next to my mouth.
Like this is good. And then just don't move from here, and it will be good.
Okay, I'm just.
Thank you.
Right.
Sorry.
In stage 3, the forces cancel, hence that's why the bead does not move. The angular velocity is an important factor in keeping the bead in equilibrium, and it's basically the angular velocity who's restricting the bead from climbing at a faster velocity. The theory is that the greater the angular velocity, the more stable the bead will be when arriving at equilibrium, and the greater the angle of equilibrium it will be, because the centrifugal force is what's helping the bead climb up the side. All right, next we're going to move on to basic principles. So basic assumptions that we're going to make is that we're going to assume that the angle at which the equilibrium angle stays between negative pi and pi, and we're using a Lagrangian Lagrangian. We are able to calculate for the dynamic of the beads by subtracting potential energy from kinetic energy, and after some derivatives, which will be shown in our appendix, we arrive at the equation r cos multiplied by g over the angular velocity times the radius. So in theory, looking at this equation, the greater the velocity at which the hoop spins at, the greater the equilibrium angle, because as we increase the velocity, the greater the denominator gets. Hence, the smaller the value inside the bracket gets. As well, the stronger the velocity, the bigger the centrifugal force. So the more it is likely to be greater than the sum of the gravity and drag, and it's only true if the angular velocity is greater or equal to the critical angle velocity. And consider angular velocity proportional to the gravity, and from this we should see a generalized force. So back to the kinetic energy minus potential energy to find the dynamics of the bead. So theoretically, if we increase the angular velocity, which is one of the key parameters, the value of our, so basically we will see an increase in the critical angle, which is also the angle of equilibrium. And this is our experimental verification taken from 5 trials and tracked using tracker and plotted with error bars using Excel. The average and deviation was calculated and shown on the error bars, and it could be seen that our experiment follows our theoretical, which states that the angle of equilibrium, or the critical angle, is proportional to the angular velocity. So this experimental verification verifies that our theory fits our experiment. Next, we're going to move on to basically the mass, which is another one of our key parameters. If we look at not only the mass but also the radius, so basically the dimensions, the characteristics of the bead, from our derived equation, we can see that basically mass and radius is negligible, or rather it's not a part of the equation. So hence, even though the mass could vary the gravitational force, since it's mass times gravity, we should see that the mass and also the radius a difference in the mass and the radius should not change the equilibrium angle at which the bead arrives at. And here is our experimental verification so we plotted angular velocity against the angle of equilibrium using 3 different metallic balls of different masses and different radiuses, which were shown earlier. And it's showing that regardless of the different masses, at each angular velocity, the angle of equilibrium is almost the exact same, which shows that the mass and the radius of the bead has no effect. Hence, our theory was correct. Mass and radius has no correlation and no effect on the phenomenon. And then to the rest of the key parameters, we already mentioned that by how angular velocity is proportional to the equilibrium angle. And then as well, we also not only do we vary the radius of the bead, but we also vary the radius of the hoop. And it does not, and it basically almost all of the data points except for the data points at a lower angular velocity, they basically overlap, which shows that the radius of the hoop does not have an effect on this phenomenon either. And there is a lot of deviation in the lower angular velocity because at that point, during that time, the centrifugal force is very little, so the system becomes actually quite a little unstable almost. So in conclusion, we talked about how we use tracker to track and Excel to graph all these motions in relation to each other, and we talked about how how the bead was theoretically held up by the angular velocity and also the friction, but most importantly, how the canceling out of the forces enables us to is the reason why the bead stays in equilibrium, and we also explored the different parameters that affected the dynamics of the bead.
Okay, thank you. 2 minutes for questions from the opponent.
Yes, thank you for your presentation. So first, I'd like to ask, how do you make the measurement?
Sorry, there's a lot of echo.
I can't hear you. I can't hear you at all.
There's a lot of echo from your end. Do you have 2 computers open?
I don't know if we do. Do we?
We have 1.
We have 1 computer, so I'm not quite sure. We'll try
Daniel, we can hear you clearly.
Now I can't hear anything.
1, 2, 3.
Barely, we could hear you. Can you say something again? Hello? Yeah, we can barely hear you. Can you turn your volume up?
Does that work?
A bit better.
Oh, is this all right?
That's much better. Thank you.
Okay, I'll try and get this to work out. All right, so yeah, thank you again for your presentation. So I'm wondering how you made the measurement labels along the side of the hoop. You made some markings on the hoop. I'm wondering how you made them.
Let me just, you meant these markings?
Yes, those markings.
They were written in with a Sharpie, and we basically also used the measuring tape. So we laid it on the bottom of the hoop, and we just like measured marked each centimeter.
Great, and if
they
you
were
could
for
go to
calibration purposes.
Right, thank you. If you could go to the slide where you show how you calibrated tracker. You set the ruler for tracker. I think it was a couple slides down. There you go. Yeah, that one. So there you appear to have set the ruler to measure a certain distance, but that's along a curved hoop. Whereas the measurement for tracker, the ruler that you've calibrated appears to be linear. Would I be correct there?
The diagram is misleading, and like I can basically just count the first 8. Like basically the calibration and the measurement of the
Okay,
ruler
I
is just
see.
like,
I see. All right. Thank you. If you could go to slide 13, please. So you call the angular velocity omega squared. Why is it squared here?
sorry, it's not omega squared, it's W squared.
Sorry, yeah. Why is it W squared instead of, say, just W? All right, that's all right. Could you go to slide 14?
Velocity is squared. Sorry. Okay, slide 14.
That's all right. Yeah, we can come back to this later. Slide 14. So I was wondering, in slide 14, do you have these things in a rotating reference frame or in a stationary reference frame?
Of course, these are a rotating reference frame because no way would the bead be like.
Great. So are there any other fictitious forces that would be acting on the bead?
Just the main forces. There definitely would be like air would be drag and stuff, but then actually no, drag wouldn't play that much of force. But these are just the main forces.
Okay, thank you. Okay, 3 minutes for preparation of the opponent.
Hi, can you hear me? Yes?
Yep, we can. You may
Right,
begin
great.
now.
I'll be opposing problem C, bead dynamics for team sigma. So the problem statement is a circular hoop rotates about a vertical diameter. A small bead is allowed to roll in a groove on the inside of the hoop. Investigate the relevant parameters affecting the dynamics of the bead. So the task to be identified. First, to develop a controlled and reliable experimental setup that allows for easy measurement and reproducible results. Secondly, to qualitatively describe the dynamics of the bead in various different situations. Third, to quantitatively model the dynamics of the bead and consider extensions to the problem. And finally, fourth, to demonstrate good experimental verification and good theoretical experimental fit and explain any deviations or trends. So here's a summary of the report given by the reporter. So we thought that there was good experimental fulfillment of the problem statement and that there are some possible theoretical expansions to what is already quite a good theoretical model. So the theoretical analysis began with some free body diagrams, and it took a Lagrangian approach in order to identify the equilibrium position. Experimentally, they began by varying angular velocity, varying bead mass, and varying hoop radius in that order. So some merits that we thought the reporter had in their presentation. First, we thought that there was a good experimental setup. They controlled the angular velocity of the hoop very well. And their measurements were made effectively in order to vary the parameters with a high level of precision. The top-down camera view allowed for an effective measurement of the system, and the markings on the hoop were good to avoid any sort of error in taking that top-down measurement due to the curved hoop. We thought that the introductory 2D theory to the system was very well explained, and we think for their parameters, they varied some relevant parameters. In terms of some possible next steps, first, it would be nice to know whether the ball during its motion, not when it's in equilibrium, is experiencing a rolling or a sliding friction. So is the bead sliding or rolling? Again, the problem statement says the dynamics of the bead. So it would have been nice to see some modeling beyond just the final equilibrium angle of how exactly the ball is going to reach that equilibrium angle in order to satisfy the problem statement. In terms of the free body diagram, there are some issues that we found with the free body diagram, not necessarily being in a static equilibrium, even though it was described to be in a static equilibrium. So we'll revisit some of the free body diagrams and make some corrections. In terms of a theoretical expansion, we're going to discuss potentially offsetting the axis of the rotation. And finally, we're going to talk about experimental error and maybe some sources that may have resulted in some experimental error in the system. So the overview of the discussion we are now going to go through. First, we're going to discuss their theoretical model and some of the issues we had with their free body diagrams. We'll then talk about the dynamics of the system and rolling and sliding friction. We'll talk about experimental and measurement errors that may have resulted during the experiment. We'll make some theoretical clarifications, and we will discuss some of the assumptions made in that theoretical model. And finally, we will discuss some potential expansions to the theoretical model of the reporter's presentation. I would now like to call up the reporter for our discussion.
Okay, you may begin.
Yes. How is my microphone?
It'd be great if you could share your slides.
Wait, is my microphone okay from this distance?
Yep, we can hear you.
Right, cool.
Great, thank you. So it'd be great if we could start with those free body diagrams. So if you could go to, I believe it was slide 14, where you presented the free body diagrams. Great, so you mentioned, so I was just wondering again, the question about, are there any fictitious forces? You have the centrifugal force, but there are 3 fictitious forces that act when you move into a rotating reference frame. So what about the 2 other fictitious forces? Namely the Euler force and the Coriolis force.
So you meant the ones other than the centrifugal force?
Right, that'd be correct.
They're negligible.
Okay, we partially agree because we found that the centrifugal force was more important, and the Euler force is not really affecting the scenario because it's rotating at a constant angular velocity. Now, specifically in the third free body diagram, there's a force of drag acting on the bead, but the bead is supposed to be in equilibrium. Can you explain to me why there would be a drag force acting on a bead that is not moving?
I'm sorry, you're talking about the third theory.
Right, so there's an FD there. I'm just wondering, why is there that FD if it's not moving?
Because it's not moving. So, like.
All right, well, we disagree there because we think that the drag force is dependent on the velocity and the air drag should vanish when it is not moving. Would you agree with that?
I didn't say anything and you kind of just went ahead, but there is no drag. This diagram actually has an error. There shouldn't be any drag. Sorry about that.
All right. And you mentioned that this diagram is in static equilibrium, but there's a friction force acting on it that appears to be putting a net torque on the system. Is there a net torque acting on the system, or would this be another potential error?
No, because it's stationary and like the gravity is trying to pull it down, but then the friction always goes against the way that the object is moving. So the friction is actually keeping it up.
Right, so we think that there's still a little bit of a net torque in the system because the friction is a force acting outside the angle of rotation of the bead. But anyways, we will move on from that now.
I'm sorry, could you draw where the net torque is? Like just pull up the...
Oh no, sure. So my point is simply that there appears to be a force that is acting, that is not acting on the center of mass of the bead, which would create a net torque. And there doesn't appear to be anything else in this model to resist that net torque.
I'm sorry,
that would stop it from rotating.
To show me where it is?
Like I don't know exactly how I could show you, but you have the frictional force little f, the light blue arrow, that is acting away from the center of mass of the object.
Could you use the annotate function at the top of the screen to show me? You can draw on the screen, like you can draw on the free body diagram.
I'm not. And I'm just going to circle the light blue arrow there. That's not acting on the center of mass of the bead. And things that don't act on the center of the mass of the bead, precisely like that, should create a net torque because there is that that moment arm. Anyways, that's all right. Why don't we move on from this into some other discussions? So I'm wondering.
I didn't mean like circle it. Can you draw the vector? Like the net torque vector. It's not circle it.
The net torque vector would be acting outside of the page. If that frictional force was acting as it is, this wouldn't be in static equilibrium. There would be a torque acting on the system. Anyways, that's unimportant now. Let's move on to the next topic of discussion. So I'm wondering whether there would be a rolling friction or a sliding friction acting on the bead.
At which, like when?
Just during its motion as it approaches its equilibrium point, would it be a rolling friction in general or a sliding friction?
I would say that there would be a rolling. Actually, upon arrival to the equilibrium point, the bead actually oscillates a bit. So it's like
Sure.
During that oscillation, it's more of a sliding.
Okay, so at that point,
it has shown that with the higher angular velocity, there is less oscillation, but then like with a lower angular velocity, the bead tends to like oscillate a lot more, especially for 7 RPS, which is 7 radians per second. That one oscillated a lot when we were tracking it from the top view.
Okay, so I was wondering, since there is a rolling friction, how did you model that in your theoretical model?
We did not model it here, but we did see it in our experiments.
Okay, so if you did not model it, would you think that it's not an important component of the analysis of the dynamics of the system?
No, I think you're absolutely right. Since the problem is focused on the dynamics of the beat and like its relevant parameters on it, I think yes, we should include the that dynamic and like that kind of motion.
I was wondering if experimentally speaking, you actually had any graphs of maybe the trajectory that the bead would be taking in order to reach its final equilibrium point.
Sorry, I don't have the graph, but I could annotate it. It's not included in this presentation, but it looks something like this. Like that's what it looks like. Just ignore this.
Okay, we agree to an extent with that. So would I be right in assuming that you don't have a theoretical model for that dynamic, for the dynamics of the bead, but only for the static equilibrium of the bead?
Yes, we didn't include it, but we did investigate motion near the equilibrium. And we got that graph from basically tracking it from a vertical view. So basically tracking every single position from like the beginning of where the hoop starts spinning all the way to when it reaches equilibrium. And so that like that graph that I drew right there also like showed the oscillation upon reaching equilibrium.
Great. Could you go to slide 22, please? I'd like to talk about, I believe there's a graph there. Sorry, yeah. So you don't have any error bars on these measurements. Is there error in these measurements?
The error bars are comparable lengths, but if we go back to slide number 16, we did have error bars for these. Let me wait, which number 2? Well, yes, there is error for these, but we just didn't include it because this is more like generalizing, looking at it as a whole and analyzing like its relationship to different radiuses, versus here we're just kind of plotting it against another variable. So
yeah. All right. So
like generally generalizely show the idea. Like we're not measuring anything. We're just showing that like the points are basically overlapping. So hence like radius of the hoop does not exactly have an effect on the dynamics of the bead.
Could you go to slide 20, please? Or sorry, 21. My bad. Yeah, so here it appears to be quite a sharp. This we think that this should be a sharper curve here.
At which point could you annotate it? Like at which, like here or here, like draw out how you think the motion, like how the angular velocity versus the equilibrium angle should look like.
Yeah, so right here, we think there should be a sharp movement from no motion into some motion, like into some angle of equilibrium. Just like that.
Can you explain why do you think there's a sharp motion? Because like when the hoop starts spinning, it doesn't immediately start off at 7 radian, like let's say like
that's just what we think the graph should look like. All right.
Could you explain? I still don't get it, because like the hoop doesn't just exactly start like spinning out, let's say like 12 radians per second. It slowly accelerates to that point.
So that's just what the arc cosine graph should look like. But anyways, I'd like to now talk about maybe just some potential. So we were wondering at the start in your parameters, you mentioned something about the angle of the axis. Could you go to your parameters at the start?
I'm sorry, I still don't get it. Can you like write out the?
That's all right. I'd like to move on to a different topic so we can maybe cover some more things before time runs out. Could you please go to the parameters you mentioned at the start? Yes. Right. So here you mentioned a tilt. What is this tilt? Could I get this, please? I'll do my best. In the meantime, could you explain what the tilt is? Yeah.
The tilt is basically imagine this, but then we put it on like a slant so that the vertical axis is like on the tilt instead of being directly down to the ground. Yes.
And what was the result of that?
We did not collect any status on it, but like any data on it, but we do predict that the curve is going to be similar to that. Like when we tilt it, it's definitely going to change the axis of rotation. So right. It would look similar to the graphs that we got from.
We don't completely agree here, because we actually found that when we changed this tilt, there was actually a possibility for resonance to emerge in the system, where the oscillations would actually increase in amplitude and it wouldn't settle down to a final equilibrium position.
Right, could you get the graph? Like,
sorry, like I don't have the graphs on me and it looks like we're running low on time. So I'd just like to say thank you for the discussion. And now I will present my summary.
You may begin.
All right, so during this discussion, the presenter, we discussed some issues with the free body diagrams presented by the presenter. So we think that the issues with those free body diagrams were definitely present, but at the same time, we think that those didn't influence the Lagrangian analysis that was done afterwards, and the Lagrangian analysis still modeled the problem quite well. In terms of maybe some experimental changes, we thought that So we thought that experimentally speaking, the experiment was quite well done by the presenter, but maybe that there could be some work done there in order to maybe collect more data on the dynamics of the system. And similarly, we felt theoretically speaking, there was great work done on finding static equilibria, but there could be more work done on analyzing the dynamics of the system. And for example, how friction, rolling friction might apply to those systems. Once again, thank you, opponent. Thank you, presenter, and thank you.
Thank you. Questions from the reviewer?
Okay, so my first question is for the reporter, which is, how did you vary the coefficient of friction? Since that was one of your parameters that you had in the beginning.
Oh, we actually used different hoops. So basically we had like a 3D printed hoop, and then we had like bamboo hoops, and then we put like nail polish, which is like type of liquor, to like make the surface a lot more smoother. And we were able to track find the friction coefficient by just tracking the motion from like dropping it from.
Moving on, which is, how did you control the RPM and yeah.
We were able to control it using the DC power supply, like with the stepper motor. Like, would you like me to share the screen?
Okay. And just to clarify quickly, both you as the reporter did observe some oscillations in the dynamics of the bead before it moved to its equilibrium point, correct?
Yes.
And the opponent would agree with this.
Yes, we'd agree with this.
Okay, so for the reporter, can you quickly point us to the free body diagram that would best represent the movement of the ball while in oscillation?
Yes.
I'm sorry, I can't. Okay, I guess if you can't find it, we can move on. And my next question is for the opponent. For the opponent, how would you personally discern the equilibrium point? And would it be any different from what the reporter has done?
Sorry, how would we discern the equilibrium point, experimentally or theoretically?
Both.
Experimentally, we followed a similar model where we tracked the bead and we were able to then identify where it slowed down and stopped moving. Theoretically speaking, we also used a Lagrangian analysis in order to find the position of the bead. We found that there were two stable equilibria for the bead, one on either side of the hoop at the same angle, and one unstable equilibrium for the bead right in the center of the hoop.
Also, my next question is also for the opponent, which is, what role do you believe that the centrifugal force plays in the bead dynamic?
Well, centrifugal force is running away from the center of the hoop, so it should act against the normal force that would push the bead back towards the center.
And the reporter would agree? Does the reporter agree?
Yes, I agree.
Okay, and my last question is once again for the reporter, which is, did you observe or do you think that the kinetic friction will have any impact on the bead?
Well, yes, because like on the friction, it would definitely change the friction force and how strong the friction acts upon it.
Okay, so thank you for
Thank
your
you.
time.
Okay. Preparation of the reviewer. Okay, you may begin.
Can you hear us?
Yes.
Okay. Okay. Hi, everyone. I'm Crystal Lee, and I'm going to be the reviewer for problem CB dynamics. Okay, so we're all well acquainted with the problem statement, so I'll be moving on. And the task that we have identified that both sides must accomplish for this problem is pretty similar to what the opponent has already identified, which is task 1, create a controlled and reliable experimental setup. 2, provide quantitative theoretical models backed up with using equations. And task 3 is to relate said theoretical models and equations to experimental data, and perhaps even provide some verification on the data. And finally, in task 4, identify the relevant parameters and discern their respective impacts on the dynamics of the bead. So this is a summary of the report. I believe that the reporter has partially fulfilled has partially understood the full has partially fulfilled the requirements of this problem, and some parts that they did well, especially with the theoretical analysis, was with the force diagrams, especially the qualitative analysis for the theory, and also the quantitative analysis and the equations backing up the theoretical model. And in terms of the experimental confirmation, the reporter went through the parameters of the hoop, varying the hoop diameters, varying the angular velocity, and the mass of the bead. And these are some of the merits and next steps that I believe that the reporter should take. They're pretty similar to what the opponent has already said, but just to reiterate, I guess, the experimental setup was well done. It was in a controlled environment, and that produced reliable and repeatable results, along with a fixed hammer point that allowed easy way to take measurements from the videos. Also, their theoretical model, especially in the 2D plane, was really good. And yeah, and the last merit I will mention is the parameter variations and how well they varied for the parameters that they did actually do. The next steps, there were a limited quantitative analysis. I would have liked to see more analysis on the impact of the centrifugal force. I also felt that this should have expanded more on the movements of the ball as it moves towards equilibrium, and explain the dampened motion of the ball in oscillations, and as well as some more error analysis. So a summary of the key points of the opposition. So they talked about the free body diagrams, also analyzed the friction and other non-conservative forces, and also expanded a bit more on the error analysis of the reporter. So merits, they did bring up a good force like torque. They did help differentiate between sliding and rolling friction. There was good error analysis, extension to theoretical model. Next steps, I also felt that they should focus on centrifugal force more. And yeah, so the opponent brought up the fictitious force, the Euler forces, and the reporter's response was negligible. I agree with the reporter in this case, since these forces are fictitious and the others are negligible. For the rolling sliding friction, the opponent brought up that these forces do exist, and the reporter's reply was that they are negligible and also unable to be calculated. I agree with the opponent in this case. And yeah, for mixed physics, I felt that they could have.
Sorry, the time is up. Yep. 2 minutes for concluding remarks from the reporter.
All right, hello, can you hear me? All right, so basically, wait, I can be heard, right? Hello?
Yes, yeah.
Okay, the opponent and I agreed that our experimental setup was controlled and that I had, share my screen real quick, and that I had a detailed qualitative explanation that could be proven with our experiments. And we were able to prove that the radius of the bead and the hoop does not matter in terms of like parameter on the effects of the dynamics of the bead. We also collected lots of quantitative data to verify our theory, and we had good theory and experimental fit. I said that sliding friction is more impactful than rolling friction when the bead is oscillating close to the equilibrium. The opponent disagreed with our free body diagram and experimental trends. We would definitely have appreciated if the opponent would have drawn the things that he thought needed to be corrected on the slide. So like that he could be clarified what he expects to be the trends and why they occurred, and also like elaborate or like explain some things a bit more. So for example, why he thought that there would be like a sharp curve on this graph rather than like a more like a gradual increase. We also had a controlled experimental setup that was agreed. Like we agreed on a controlled experimental setup that we were able to vary the speed and the stepper motor and the driver. We also clarified that our error bars, what our error bars meant in the discussion, and the opponent asked for the effect of the Euler force, and we said that it was negligible, and the opponent and the reviewer agreed. That's it. Thank you to the opponent and the reviewer.
Okay, thank you. Questions from the jury?
I have two questions. One is for the opponent. What is the Coriolis force and why did you bring it up?
So when it moves into a rotating reference frame in general, we expect there to be three fictitious forces: the Euler force, the centrifugal force, and the Coriolis force. We didn't get to discuss that too much in our discussion, but really the Coriolis force here doesn't matter. And the reason for that is it acts sort of into the plane of the hoop. So it would just push it against one of the sides of the groove, which may increase friction. But since there wasn't a dynamic moment,
Okay, and to the opponent, you mentioned, or not the opponent, sorry, the reviewer. You mentioned that you agreed with either the opponent or the reporter that there were other non-conservative forces at play here. My question is, what does it mean for a force to be non-conservative? You're muted, I'm not sure if you know.
Sorry. Non-conservative forces in this case would be forces that would overall take away from the total energy of the system. So I guess an obvious example would just be friction, or the force of drag, which was present until the ball stopped at the equilibrium point.
Okay, thank you.
I have a question for the opponent. So the graph where you wanted to fix the reporter's graph where there should be a sharp curve, the relationship between the angle and the angular velocity is through cosine, right? So from my understanding, cosine is like a smooth function. So why should there be a sharp?
Right, so I hope you can see our screen. So cosine is a smooth function, but this is the arc cosine. And it just so happens that like the arc cosine itself is not really defined before this point. So you'd have a straight here because it wouldn't really have an equilibrium angle above zero. And then suddenly at a certain critical value, you would begin to have these two static equilibria that are at a certain angle away from the base of the hoop. So that's what I was trying to get at. And I know I didn't explain that too well, so I apologize for that.
I had a question I had two questions, so real quick. Firstly, for the opponent. So there was a free body diagram where you said that friction is not acting at the center of mass, which there's an effective torque on the system. So how would you balance that torque since you only have your four forces, which is friction, gravity, normal, and centrifugal? So which of these balances the torque caused by friction?
Well, really, that's a static friction term. So in terms of balancing the torque caused by friction, we think that there are still small oscillations, so it really switches into a sliding mode. So it never truly settles down to its equilibrium, but it gets very, very close.
But torque causes rotation, right? So you're talking about sliding. So what is it rotating according to you in equilibrium while it's oscillating?
Well, it should be rotating slightly, but
all right, I'll just move on to my next question. So my next question was for the reviewer. So everyone's talking about this cosine graph and arc cos. Looking at the free body diagram, do you see any problem with the arc cos equation that they bring about using the Lagrangian mechanics equation? This is for the reviewer, so Upsilon.
Right, sorry. From the force body diagrams, the reporter did mention something about using the Lagrangian equations to take into account all those various forces that they listed, and then putting them into Lagrangian equation to get our cosine. I personally couldn't hear much of the reporter's presentation at this point, so I can't really comment on that. Sorry.
Do you think there's something missing? This is one thing that hypothetically, if you have to make that equation more exact or more precise, which is the one thing that you would like suggest should be added?
The arc cosine equation obviously depends a lot on the equilibrium angle of the ball. I guess to make it more precise, they could have taken a more direct approach that didn't involve going through like several levels of calculus and derivatives to get that final equation.
All right, thank you.
Just as a comment for the opponent, when you ask a question, you have to give time for your opponent to reply. And if you find that you are running out of time because you feel that the reporter is, taking too long to reply, then you will need to better prioritize your questions. Okay? We're looking for quality, not quantity. Don't barrage. We're looking for good quality.
Isn't the discussion section all about discussing? So can't the question section just be like them throwing out all their questions that they want to effectively discuss and then ask the reporter to respond?
Yes, but I think you should give the reporter time, because multiple times the opponent was like, "Okay, I'm done. Let's move." I'm done. It's like, you have to let the opponent, the reporter respond.
Makes sense.
So I did have one question for the reporter, and that is, are there any forces missing on your free body diagram based on your experiment that you actually conducted?
Oh, hello? Wait.
Hi.
Hello? Okay, sorry. No, there aren't. Those are the forces that are like, because like Euler's force and like the Coriolis force that the opponent mentioned is negligible.
Okay. I agree that those forces don't belong on your diagram, but what I was looking for is in the picture of your setup, the bead is resting against a wall that's perpendicular to the motion. And so your normal force being drawn as only having a component inwards can't be the case, because it's also in contact with this wall that you haven't drawn in your picture. I don't know how that would affect the dynamics, and I don't think it would. But so your free body diagram is neglecting that like other direction of the wall that's on your setup.
Okay, did you mean like drawing a tangent point to show like for the point of contact? Or like
I meant, so it's actually not visible in these pictures. If you go to a photo from your actual experiment.
Which one?
Yeah, that one would be great. So if you look at where the bead is on the hoop, it's staying up against this wall that's at the bottom in this view. And so that wall is also exerting a force. And so I would have been convinced that you've analyzed all the forces if you included that force that's propelling it to keep traveling in the circle.
So also like the normal force like from the side of the plastic, like not just from the hoop?
Exactly.
Okay, okay.
Okay, are there any more questions? No? Okay, if you're done with your grades, if you could just message done in the chat, and then we can get started. Okay, I think we can get started, and then if you're not done, we'll just come back to you. So for the reporter, Daniela, your partial scores, please.
6, 1.5, and 0.
Thank you. Carlos?
Yes, 6, 2, -1.
Okay, thank you. Neil?
6, 1.5 minus 0.5 for a total of 8.
Thank you. Darby?
4, 2.2 -0.
Thank you. Jesse?
Sorry, I just had to find the unmute button there. 5, 2, 0 for a total of 8.
Thank you. Kyle?
I have 5, 1.5, and minus 0.5.
Okay, thank you. Sheetal?
It's 4, 2, and 0.
Thank you. Abdullah?
6.5, 1.5, and minus 0.5.
Thank you. Michael?
6, 3, -1 for a total of 8.
Thank you. Okay. Oh, 6, 3, -1.
Oh, sorry, 9. Yeah, you're right.
Okay, cool. Thank you. Okay, for the opponent, Daniela?
2, 3, 3.5, and 0.
Thank you. Carlos?
Yes, 1, 3, 2, -1 equals 6.
Okay, thank you. Neil?
1, 3, 1.5 minus 0, total 6.5.
Thank you. Darby?
1.3, 3.2, 2, 0, total 7.5.
Thank you. Jesse?
2, 3, 4, -0 for a total of 10.
Thank you. Kyle?
1, 3, 2.5, minus 0, so 7.5.
Okay, thank you. Sheetal?
0.5, 2.5, 2, and 0. So that should be 6, yeah.
Thank you. Abdullah?
2, 2.5, 2.5, and 0.
Thank you. And Michael?
Yep. 0, 3, 2, 0.
Thank you. Okay, for the reviewer, Daniela?
Oh, yeah. 1.5, 1.5, 1, 1, 0, 0.
Okay, thank you. Carlos?
1.5, 1.5, 1.5, 1, +1, -1.
Thank you. Neil?
2, 2.5, 2.5, 1, 0, 0 for a total of 8.
Thank you. Oh, 1. So initial one, 2, 2.5, 2.5, 1, 0, 0.
Yes, does that add up to 8?
That's 9.
Sorry, 9.
Okay, thank you. Darby?
2, 1.6, 2, 0, 0, 0.
Thank you. Jesse?
1, 2, 2, 1.5, 0, 0 for a total of 7.5.
Thank you. Kyle?
1.5, 2, 1, 1, 0, and 0 for 6.5.
Thank you. Sheetal?
0.5, 2, 2, 1, 0, and 0. So the total should be 6.5. Yeah.
Thank you. Abdullah?
2, 2, 2, 1, 0, 0.
Thank you. And Michael?
Yep. 1, 2, 1, 1, 1, 0.
Thank you. Okay.
Yep.
For anyone who would like to comment, feel free to go ahead while I submit these scores.
So for the opponent, whenever you have things in which are not in rotational equilibrium, it's the normal that always shifts in order to bring things back into rotational equilibrium. So friction acts against only translational equilibrium usually and normal. So both of these are components of what we call the contact force. So it's only the normal that they have to change the direction of. And for the reviewer, an amazing point raised right there, that you don't need Lagrangian mechanics to solve for equilibrium. The simple free body diagram, if you just take into account the friction and use that to solve for angle, you'll get a way more exact formula, which will exactly tell you what the angle is, and it will fit the graph better also, I believe. So that's it.
I just wanted to say to the reviewer, the only spot where you really lost marks for me was in the discussion analysis. You ran out of time, so I felt like I couldn't give points for something I didn't hear.
Would anyone else like to give feedback, or is that it?
That's it for me.
Okay. Awesome. So we'll take a few minutes just to calculate all the scores and we'll be back. But congratulations to all the teams for completing the finals.
Now that the marks are up, out of curiosity, are the 3 teams all from 3 different schools? They should be, right?
No, Upsilon, Sigma.
Sigma and Upsilon are from the same.
Ah, okay.
Hey, Dave. I think it's fair to say that we can probably start the awards ceremony at 8:25.
Yep,
Is
that
that
seems
all right?
reasonable. Yeah.
Yeah. Okay. So I know that Dr. N is already here with us. I'll just check to see if Professor Bailey is here.
Do jurors need to stick around for the final results? Some are asking.
I mean, they don't have to, but if they want to, they could certainly stay for like some more time, I guess. Oh, I think Professor Bailey is here in the call as well. Okay, I'll just send a message in the Discord server telling everyone that our award ceremony will start at 8:25, hopefully.
Sorry, hi Jim. How long is the award ceremony going to be?
Approximately like half an hour.
Wait, then is it fine if we're not all completely online since we have to leave the school now?
I highly recommend that your team stick around. I really do.
All right.
Not to hint at any results or awards or anything, but I strongly recommend that you stay.
Why? Do they lose if they don't stay?
No, they don't, but they probably, yeah, they should probably stay. If they left, they will regret it, I'm sure.
They will also regret it if security kicks them out.
It's okay. Like
Jim,
CaYPT, yeah.
do
Pardon?
jurors have to still send score sheets?
No, they don't have to send score sheets. I mean, we literally just enter the scores in front of everyone, right? So they don't need to send the score sheets anymore.
Team Sigma, what's behind the name of your team?
Okay, yeah. Yeah, well, actually, our name is like, we had 3 teams in our school. There were teams Upsilon, Theta, and Sigma, and they spelled BTS. Yep. Very creative.
Yes, very creative.
What happens if next year you guys decide to send like 4 teams?
Completely quiet, no solution.
Then maybe we'll pick an actual letter. I don't know.
Hopefully we should start to see an increase in the number of people in this call. Hopefully, when everyone arrives for their awards. Dave, how are the score calculations going?
I'm not doing anything. It's all Andrew.
Oh, it's all Andrew.
You just have to click some buttons, right?
Yeah, I just click a button and then it's done.
See, I kind of have to make my award ceremony slides. So,
Okay, well, just pretend we're still calculating then.
What? Okay. You guys know that our stream actually has a lot of viewers. Our stream have been already played back like about 550 times. And we got like 20 likes already. Okay. I think the scores are in. Let me take a look.
Can I approve all of the selective match score sheets, or are you still waiting on numbers from
No,
jurors?
just approve everything. Yeah, please. Well, Andrew, just to confirm, our results are out, correct?
The finals are out. Selective match, we're still dealing with.
Well, selective match, I'll leave that to you then. Okay?
Okay. Okay.
So let me see. This goes here. This goes here. Hopefully I can make it to the... I think I am ready. So I will share my screen then, and we will get started with the award ceremony. I have 34 people here. Hopefully more will be joining us soon. Okay, is everyone able to see my screen?
Yep.
Yep. All right. Cool. And just give me 1 second. Okay. Yeah, so we can see the slides. All right. That's cool. So, all right. I'm gonna turn on my video as well. All right. So welcome to the closing ceremony and the award ceremony of the 5th Canadian Young Physicist Tournament, CaYPT 2021. And first, we will be presenting our team awards. So our team awards, first, we would like to congratulate the team, We Who Shall Not Be Named. Okay. And their team captain is Alex, with their team members being Ellie, Harry, Luca, and Samantha. Well, I guess they're not in the call, but that's okay. They're probably watching the stream, I hope. Next is Team Lonsdale, with their team leader, Lee Wei Su, team captain Stephen, and team members Alan, Alexander, Nicholas, and Jalbo. Next up, we have Team SMUS. Team leader is Eric Donatelli, and team captain is Zach, with team members Felix, Jay, Joshua, and Pufa, I believe. I'm not too good with names, but yeah. So next, we have Team Theta with Ms. Vanderkamp as the team leader juror. Their team captain is Adrian, with Archie, Braden, Emily, and Sophia as their team members. Next, we have Team Perturbation, with the team leader juror being Ali Reza Rafi, and team captain is Richard, with team members George, Yiming, and Ziyu. And we have Team MGCI Team 1. Their team leader is Sabrina, and their team captain is Hector, with team members Anthony, Ino, Jackie, and Wen Zhao. And next we have the team's award, and we have the bronze medal winners. Our bronze medal winners are Team Schrodinger's Wildcats. They are from White Oak Secondary School. Are you guys there in the call? Anyone from Team Schrodinger's Wildcats? Okay, maybe turn on your camera and wave at everyone.
I think open our camera. Are you sure?
Yeah, sure.
I'm not in a very good place right now, and I think, yeah.
Okay, that's fine too. Okay. Oh, cool.
Okay, just that.
Congratulations. All right. Next we have Team Schwarz Children. They're an independent team. Maybe you guys can turn on your cameras as well. Anyone? Okay, I guess they might not be in the call, but congratulations to you guys. And we also have Team Tetraquarks from Victoria Park Collegiate Institute. Are you guys in the call? Okay, wave at everyone. Congratulations. We've got some thumbs ups. Cool. And we have team awards, silver medals. So we have 2 silver medals this year. Okay, as you guys might know from the results. First, we have Team Upsilon from UTS. You guys are in the call, correct?
So we actually got kicked out of our school. So we're just on the Zoom calls on the drive home. But thank you, thank you.
Okay, cool. Congratulations to your team. Yes. And we also have for silver medals, Team Anti-Quarks. Anti-Quarks, are you guys there? Congratulations. Okay, cool. And finally, for our gold medal, we have Team Sigma from UTS.
Thank you.
Thank you.
Are you guys kicked out of your school too?
Got kicked out of our school.
Okay, but stay in the call. Okay. We will have some individual awards. So for our first 2 individual awards, we have our CaYPT Best Theory and also Best Experiment Award. So let me again introduce our guest, Professor David Bailey. So I'm just going to say the words again for those viewers that are like international. So Professor Bailey is a professor of physics at the University of Toronto that specializes in experimental particle physics and physics education. He is the chair of the U of T Physics Department Outreach Committee and also is a member of the CaYPT Problem Selection Committee. And Professor Bailey and U of T Physics have been extremely supportive of CaYPT since our first tournament. So let us welcome Professor Bailey to announce the winners for the Best Theory and Best Experiment Awards.
Thank you. So the CaYPT Best Theory Award recognizes the most in-depth and unifying theoretical analysis from the entire competition. And I'm very happy to present this award to Abe Wine from Team Sigma for their work on Problem D spin drift. this is a great problem that shows, as Einstein himself discovered when developing general relativity, that when you go from a flat system to a curved system, all sorts of interesting theoretical problems and possibilities open up. So congratulations to Abe Wine from Team Sigma.
Thank you very much. That's great to hear.
Congratulations. So next, we have the CaYPT Best Experiment Award that recognizes the most creative and effective experimental setup from the entire competition. And even when something seems like conceptually simple kind of measurement to do, it can often be very difficult to implement and get right. You know, it's even the simplest things are challenging. And I'm very happy to present this award to Shuyu van Kerkwijk from Team Sigma for their work on problem B, irreversible Cartesian diver. Congratulations.
Appreciate it.
Great job.
Thank you so much, Professor Bailey. And next, we would like to present our other individual award, which is our leadership award. So let us welcome our second guest speaker, Dr. Sacha Nokovic. So Dr. N is the founder and president of STEM Fellowship, the parent organization of CaYPT. So STEM Fellowship is a student-run Canadian charity organization that uses mentorship and experimental learning to equip the next generation of change makers with indispensable skills in data science and scholarly writing. Dr. Nokovic is a data science and interdisciplinary education expert and innovator. So let us welcome Dr. N, and he will be presenting our leadership award.
Good evening, everybody, and it is my pleasure to present Canadian Young Physicist Tournament Asadi Larry Leadership Award. The award recognizes extraordinary leadership and commitment, and is in the memory of the founder of Canadian Young Physicist Tournament, Mohammed Asadi Larry, my personal friend, and actually he himself was one of the top players on the Iranian team before coming to Canada. Unfortunately, it was a tragic event who stopped his successful academic career, and it is a proof of the competition that Mohammed was second-year medical student. So your skills which you acquire through this competition are actually the guarantee of your success regardless of the field you would be applying it to. This award will be presented to Hector Chen from McGarnaugh Collegiate Institute Team 1 for being the team captain of the youngest team by average student age. Congratulations.
All right. Thank you so much, Dr. N, for presenting the Asadi Larry Leadership Award. So I would like to give a few concluding remarks. So before that, I would like to make an announcement. So there is an individual selection stage to the CaYPT after this competition. So students will be asked to submit their presentations to compete for a spot in the CaYPT National Camp and ultimately for a ticket to IYPT representing Canada. We will be sending out emails about this program in several weeks, and your certificates and medals will be mailed to you. You will probably receive it in April. So I would like to congratulate all of the teams on your achievements. The 10 problems of the CaYPT will be the most challenging physics problems you will see in high school, and you have all achieved something that seemed impossible just a couple of weeks ago. It is extra impressive considering that most of your experimental work are done at home. CaYPT is not only a stage for you to show your physics knowledge, but it is also the opportunity for you to collaborate with others and make friends of a lifetime. I think Dave can prove me right on this. And more importantly, this experience allows you to know your potentials and learn just what you're capable of. And I believe that once you've overcome the challenge of CaYPT, there's nothing else that you cannot conquer in your future endeavors. I would like to thank all of the team leaders and team leader jurors for spending your own time to supervise your team. CaYPT is a physics competition, but it also requires a lot of organization and logistical support. And it is even more apparent during this pandemic. And your team's achievements would not be possible without your amazing work. We must also thank all of the jurors for your diligent work, especially the experienced jurors for helping us run the tournament as chairs. Your suggestions are extremely valuable for the students. In addition, we would also like to thank all of the parents of the competitors. It's one thing to support your child with studying physics, but it is truly unbelievable for you to allow your child to do some experiments at home. And next, I would like to thank our committee members as well. First, I would like to thank Ryan for helping us coordinate this event for now the 6th year. He's been with CaYPT every step of the way, ever since being my team leader in IYPT 2016 to Team Canada's first place in online IYPT 2020, and now for our first fully online competition. Next, our student committee members, in particular, Dave and Andrew. As many of you know, Dave is our student resources team lead, and he arranged multiple calls with the teams before the competition. His encouraging words and thoughtful advice kept many teams together and allows us to have a record-breaking number of participants this year. Andrew is our hero behind the scenes. He is our information team lead. Andrew led 6 high school students who developed our CaYPT management system. It is the backbone of the entire competition. Without it, our online competition would not be possible. The fact that our system is developed by a few like grade 10s and grade 11 students sort of amazes me every time I think about it. And also special thanks to Hannah, Harry, Leo, Nathan, Darren, Patrick for timing. And thanks to Tony for designing our certificates and plaques. And finally, I would like to thank our 2 guest speakers. Again, Professor David Bailey from U of T and Dr. Nukovic from STEM Fellowship, and all of our partners for your continued support of CaYPT, even through these challenging times. So last year, we narrowly missed the lockdown by about 2 weeks. This year, we meet in this special way, and I hope that next year we will meet again at U of T Physics. And I would like to declare the official conclusion of the 5th Canadian Young Physicists Tournament 2021. I hope that everyone have a great rest of the weekend, and competitors get some sleep if you pulled an all-nighter. Thank you.
Thank you. Good night, everyone.
Good night, everyone.
Thank you.
Thank you.
Thank you.
Come on,
I
Abe.
see her. Go.
Good night. Thank you.
Thank you, guys. Thank you guys so much. It's yeah, it's another year, guys.
You wanna stop the stream?
Yeah, sure. They can see our behind the scenes if they want. I'll stop the stream. All right.